So welcome, first of all, to this sixth annual virtual pickup workshop. Uh, we do these online workshops for different topics, but also for people who, for whatever reason, would like to do a virtual workshop. So this is our sixth annual one, as I said. We do, if you're unfamiliar with pickup, you'll have a chance to learn a little more about it at the wrap up at the end of the week on Thursday. So I'm not going to go into pickup too much other than it's the Partnership for Integration of Computation in Undergraduate Physics. The key word is partnership there. And we consider you part of a partner by simply joining and completing a workshop like this. So if we do workshops in person around the country, and you'll hear more about this. If this were an in-person workshop, there would be a special ceremony and we would anoint your forehead with oil. But since it's online, a pickup priest on Thursday will just wave their hand in front of the camera, and you'll be official pickup partners. All right. Anyway, more about pickup later. Let's get into some of the logistics here. If you are not familiar with this gather town, you probably have noticed you're assigned a little icon that you can use the arrows to move around with. I am currently located in the front on those green carpets in one of the central podiums there. And by virtue of me standing on those green carpets, if I'm not muted, everybody in this entire space can hear me. If I were to walk off of that and just be on the gray area, then nobody could hear me unless you were standing right next to me. So anybody standing on the green carpet up front can be heard by anybody, and anybody in the space can hear you also. You'll notice there's also 8 colored, that has the word group. There's 8 of those. Those are sort of like breakout rooms where if you're standing in there, everybody in that space can hear you and you can talk to everybody in there. If you're outside on the gray area, you cannot be heard in that private space, right? And then you'll notice at the bottom there's a bunch of chairs. The chairs are just there for decoration. Anywhere in the gray, unless you're standing directly next to someone, nobody will be able to hear you. If you are standing next to someone, only the person you're next to can hear you and interact, right? But remember, anybody up front in that green space can be heard by anybody in the room, right? That's the basics. There's one other thing to point out that's going to play an important role in if you look down on the right, there's a few little icons. If you hover over them, there's one called info board. It looks like a sign attached to a little post. There's a bunch of important information up there. If you click it, it says pinned messages and announcements. If you highlight the pinned messages, there's several places of interest, and I think I'll just go through very quickly and tell you what's there. You can look at this, but this will be these pinned messages will be referred to as we go through the workshop today. Right, so there's contact information. If you want to enter your contact info for collaborating purposes, either during the workshop or after, you can enter that. There's a website on the pickup website. The workshop website has the agenda for today, the specifics, and we're going to try to stick with the times there. And there's also there's a Google Drive for workshop shared materials where you can pop things up for sharing and for demonstrations. We'll come to groups a little bit later. There's a spreadsheet to help determine who's going to what groups. And as far as the small groups later in the day, there's a description of each one and where on those colored group carpets we're going to meet. So look at that. There's a lot of info up there. All right. And again, we'll allude to that throughout the day. Should you have any troubles or want to ask something, we're going to start out with a series of presentations. I would suggest the proper way to do is the presenter will stand up at one of the podiums, and so there, if you look on the website, you can see who the uh, organizers are. It's me, Kelly is my name, Walter Freeman, Larry, Patricia, and Nick Nelson. And if you see any of us, I'll probably stand off in one of the corners or off to the side. If you see any of us, you can always walk up to one of us and ask a question if you're not sure about something. There is also a chat feature, by the way. You can get to that in the lower right also. Right. It's pretty intuitive. If you have troubles, try to find one of the organizers and we can help you out in some way. All right. So as far as the schedule goes, we're going to try to stick close to the times. And again, you can get to that from the info board. If you click on the workshop website, it has a detailed schedule for the day. And again, I said we're going to start out with several presentations, and we're going to try to stick close to the time. This is going to be difficult because faculty, I know you like to interact and ask questions. I would suggest let's unless the presenters have finished early, we may have time for a question or two. I would say write down your questions and hold on to them until we get into the small groups a little later. You'll have a lot of opportunity to interact with everybody who's presented something. Furthermore, tomorrow's part of the workshop, we've tried to tailor this workshop where today is the longest period, and we'll try to accomplish as much as we can. Tomorrow, starting at noon Central, is entirely dedicated to addressing whatever questions you have, and we call it sort of office hours tomorrow. All right. So, and then Thursday, as you'll see, is for presentations that we'd all like you to do. So, to get the most out of this online workshop, today's kind of a busy day, a lot of info. We're going to give you a homework assignment. Right. I think this is what we've come up with to make this online experience most effective. Of course, the general topic is AI and using AI to learn physics, but the assignment is simply to come up based on being inspired or something you've already thought about and you want to try, come up with a plan for doing something regarding your students coming up this fall learning physics with AI. And tomorrow's session is to get questions answered, assistance of any kind, if you want to hang out with the group leaders. And then Thursday, we'd like you to give a little presentation, short little presentation, more details on that tomorrow. No, actually at the end of the day today. But just basically one slide about a 3-minute presentation on what you plan to do. It doesn't have to be a particularly well-developed idea even, but just something you've conceived of, perhaps you've already thought of, or something you've been inspired to do here. But we've conceived that this is one of the probably best ways for you to actually get something out of this workshop and keep you engaged, even though it's predominantly online. All right. So it's 12:10. I'm supposed to hand things off to Larry now. And again, I'm going to try to keep things going on time. I know it's difficult to keep faculty on time. So that's going to be my role throughout the day. Larry, go ahead and hit anything that I have left out, and then start out with what you're tasked to cover.
Great. Good job,
All right?
Kelly. Are you able to hear me? Yeah, good. Okay,
Yep.
great. Yeah, Kelly did a really good job actually of going through everything. Nicely done, Kelly.
Yeah.
Maybe
Yeah, flattery is going to get you nowhere anyway.
the one thing that I'll add is that with the chat, if you have any questions at any time, go ahead and make use of that. And on the info board, do go ahead and look right away at the description of the groups, number 1, number 2, number 3. And then if whichever of those there's the most of, we can also have a 4th group as sort of an overflow of one of those. And so just be thinking about that, because it's going to be up to you based on your interests of how the groups get divided up later on. And the one other thing to know about in terms of logistics is we are recording this. So be sure to keep any profanity and etc. to a minimum here as we go throughout the day. Um, all right, so the next thing that we're going to do is I'm going to give a very brief intro to some terminology related to AI and LLMs, and then Walter's going to go into more detail about that. So let me share my screen here, and you should see an sort of infinity thing popping up here first, and then you should see a slide that says quick intro to AI and LLMs. So if you don't see that, please holler. So I'm assuming that everyone sees that. And so as everyone I'm sure knows, AI is artificial intelligence, and just a few historical highlights here that people might remember. It was back in the 90s that IBM's Deep Blue beat the world champion in chess. And then more recently, DeepMind's AlphaGo beat one of the top humans in the game Go. And DeepMind is actually Google's AI division, who also a few years later than that developed AlphaFold to solve the protein folding problem. So now we're actually getting into science here, and this is a big deal. So their Nature paper from 2021 has about 40,000 citations, and they received the 2024 Nobel Prize in Chemistry. Okay, so this was just a wee bit of history very, very quickly. And then around the same time, ChatGPT arrived. So this is an example of a LLM, which stands for Large Language Model. So the couple of examples there specifically of AI are sort of specialized tools at playing games or solving certain tasks like protein folding. But an LLM is a more generalized thing. And so in terms of large language models, you'll see some of this as we go throughout the day today, that the big tech companies have these things called LLMs. So you've heard of ChatGPT from OpenAI, and you're going to see an example shortly of using Claude, which is another LLM from Anthropic. You'll also see an example of using Gemini, which is another LLM from Google. And then, not to be outdone, the other big tech companies are also involved. So Facebook's parent company Meta has their own called Llama. This is Elon Musk's AI company, XAI, has Grok. Microsoft has a platform here that plugs various different LLMs for people to be able to use. And Copilot is Microsoft's tool that you can use along with Microsoft things, including GitHub for coding. And Apple has something called Apple Intelligence, which, for example, is plugged into Siri to help Siri work better, as well as, I think I saw a commercial yesterday for how you can subtract cats from pictures using Apple Intelligence. And in addition to these, this is an international game, and so a couple of other popular ones here. Minstrel AI is in France. And here's a couple of popular Chinese ones from Alibaba. And DeepSeek made news not too long ago for being a apparently much cheaper version. They were able to train it without nearly as much resources as some of the other ones. So continuing on here in terminology. So when you interact with an LLM, a large language model, you provide some text to it. So this is called a prompt, is the text that you provide. And then what happens is that under the hood, it breaks that text down into what's called tokens. And so you might see that something costs 500 tokens, for example. We might hear more about that a little bit later. A few other terms. So the context is what the LLM knows about from your earlier interactions. So one thing that, if you've played with these at all, you've probably found is pretty slick, is that as opposed to a Google search where it only knows your current search, if you're interacting with the large language model, it knows about the previous things that you entered and that it told you and can make use of that context. So that's what that word there means. A system prompt is the original set of instructions that it has. So it provides the persona of what its task is and how it's going to act. APIs, this is something that if you're doing coding, might be of interest, that these are libraries that allow you to interact with LLMs and put them into your code. So for example, ChatGPT has APIs that you can use to be able to allow the user who's running your program to enter a prompt and receive a response from ChatGPT. And you'll see an example here also about the use of agentic AI. So agentic means that you now are giving agency to this AI tool for it to be able to go out into the world and do things. So an example of this would be if someday in the future you had an AI assistant that every morning before you woke up, it went through all of your emails and deleted the unimportant ones and replied to the ones that need an obvious reply, and then summarized for you what you have left in your inbox. Now, what you're going to see today in terms of agentic AI is using an AI tool to help with programming where you give it some agency also. And then beyond this, of course, in the future, we don't know what's going to happen, but some terms that you might have heard are AGI and ASI, stands for Artificial General Intelligence, which we're not there yet, and Artificial Superintelligence. So this is where the system that you would interact with is as good as any human PhD throughout all fields that you get to, so that then it can build upon itself to make an amazing system that could potentially overthrow humanity. So hopefully that doesn't happen soon. If you're interested in more technical details after today's program is done, here's a couple of resources that you're invited to make use of. So on YouTube, there's a series of videos from 3 Blue 1 Brown, which gives a really nice visual explanation of how neural networks work for AI. And then this is one that's within that series specifically on LLMs. So these are a nice set of videos. And then earlier this summer, a faculty member from the University of South Carolina gave a course on specifically using AI programming with PyTorch. And his resources from that workshop are available here. And these slides, I will put them in that shared Google Drive folder that's linked from the info board down towards the bottom right corner. So you'll be able to access those later. So I'm going to go ahead and stop sharing now, and then I'll turn it over to Walter, who will be going next.
All right. Hi, folks. Can you hear me okay? All right.
Yep.
So I am, unfortunately, down to the wire in preparing my presentation, but I think I am ready. So give me just a minute to get everything set up. Let's see, how do I need to figure out how to screen share things. All right, so here we go. There it is. Okay, so I decided that I would title my presentation AI Ecology as something of a prelude to another presentation that you will hear a little bit later, that has a theme of AI biology. And what I mean by AI ecology is when you are using AI, what are you really interacting with? What happens when you type that query into ChatGPT? And specifically, I want to talk about how this is radically different than the way that all of us have grown up with computing being. And the role of AI in the computing ecosystem is very, very different than what we're all used to, because computing has been democratic for the last 40 years for my life, right? When I was a child, my grandfather bought his 2 grandchildren computers from Gateway 2000. They came in big cow boxes, if you remember those. They cost on the order of $10 to the $3. Now you can get one on the order of $10 to the $2. And those computers could really do almost anything interesting. The hardware is pretty much all modular. You know, you can go buy parts to your computer at Best Buy, swap them out. And the software to do anything is open source. I'm running all open source software on my own computer. You can too. And the tools to make that software are also open source. Well, the internet has been a transformative thing in computing, but anyone can buy access to the internet and run a server. So maybe you hire somebody else to do some of this for you, right? Maybe you buy a pre-built laptop. Maybe you hire someone else to write code for you and you purchase the computer program they have written, but you don't have to. The pre-AI computing ecosystem is very open, very democratic, very accessible. So in a cartoon, anyone can walk into Best Buy with $500 and buy themselves a laptop. Then you can take a laptop, you can combine it with an operating system like Linux that you can just download, combine it with C or Python, and then you could write any software you want, pretty much, right? There, like you can walk to Best Buy, walk back, and download a Lattice QCD code onto your computer and run it, or you can write one yourself. And there's nothing stopping you from doing that. And even on consumer hardware, you can do useful Lattice QCD simulations. And then you can combine that with an internet connection to make the interconnected internet world that we have today. You can go put a website. This is something that I think a lot of our students don't realize, that you can, using your own laptop, put a website on the internet for everyone to see. And you're not doing any sort of cloud computing. You are the cloud, right? You're not relying on anyone else's hardware or software to do any of that for you. But the modern world of AI and large language models breaks this streak of democratization. And this is a matter of great concern for those of us who are invested in open source ideas. So frontier AI capability, like what you're using when you're talking to ChatGPT or Copilot or Gemini or whatever else it is, requires vastly more resources than any of us have. It is, and I'll give you numbers on the next slide. It's also critically not open source and not open weight. When you're talking to ChatGPT, you do not have access, even if you had the hardware to run ChatGPT, even if you were to go purchase a big stack of GPUs from NVIDIA, open, in scare quotes, AI will not tell you what the weights for ChatGPT, the most modern version of ChatGPT are. Just to be clear, when I say weights, the weights in a large language model are a set of floating point numbers that talk about the interconnection between neurons. So when you're using one of these models, they cannot learn when you're talking to them. They are pre-trained by OpenAI or Anthropic or Google or whoever else, and they have this blob of linear algebra that is called ChatGPT, that contains all of the intelligence of ChatGPT. And if it looks like it's learning things when you're talking to it, that's only because you're adding to its context, right? But that set of weights is fixed. And OpenAI will not tell you what they are, at least not for the frontier models. They also won't tell you how they trained them in full detail. They will say, yes, we let it read the entire internet, and we let it read the comment history of Reddit. Yes, these things are trained on Reddit. That's vaguely horrifying. Instead, you talk to them via a cloud interface. So the way this works is your computer sends a query to a data center that one of these companies runs about a whole bunch of GPUs in that data center. Think, I don't fully know, they won't tell us, right? But somewhere between $100,000 and $1 million worth of hardware wake up, they see your query, they write an answer, and then you get an answer back. That's how that works. So how much does this cost? A lot of people kind of speak sometimes in sort of apocalyptic terms about the energy use of AI. And so I wanted to give some ballpark measurements here. And it's important to distinguish between training and inference cost. So the training cost is a one-time cost paid by the company that runs the cloud model. We call these frontier models, where they feed this thing all of Reddit, all of Wikipedia, every piece of text they can get their hands on in a process called pre-training, where they teach it to speak and teach it basic logic. And then they do what's called fine tuning, where they give it a query and then see what it says, and then either say good robot or bad robot. And there are lots of techniques for making this more efficient. I can talk about them if you want me to. So that's the training cost. And oops, I have 100 million miles, which is not accurate. $100 million is what I mean. So it costs about $100 million to train the most recent version of ChatGPT. And the energy I've decided to convert into how far could you drive on that energy. You could drive halfway to the moon, 100 million miles, on the amount of energy that it took to train GPT-4. But inference costs are much cheaper. And I've done this here per 1,000 tokens. They'll charge you about 1.5 cents for every 1,000 words that these models spit back to you. That's not nothing, but it's also far less expensive than the training cost. So, there's the saying that if you're not the customer, then you're the product. So with these companies, either you're paying them, right? Paying them per token, paying them a subscription fee, whatever, or they're making money off of you in some way. And that's much cheaper. So to generate in energy as well. So to generate about 1,000 tokens uses about 15 watt hours. That's the amount of energy that it costs to drive about 100 meters. But compare that to a Google search. Googling something is 0.3 watt hours. So far, far less energy. Just wanted to give this ballpark table. Larry already introduced us to some of the companies that are doing this. I want to kind of highlight a few of them and highlight where they fit into this this continuum between things in the cloud versus things you can do yourself. Because the punchline is that some of these things are more accessible on your own hardware than you may think, or they're getting that way. OpenAI, which is really Microsoft under the hood, their big product is ChatGPT, which we're all familiar with. They are a commercial first company. They want to commercialize these products to help Microsoft sell Windows and also to make a bit of money doing it. Anthropic is a spin-off company from OpenAI. It was founded by OpenAI employees that said, we want to start our own company. Their emphasis is on AI ethics safety, AI research. They're still not open weights. You cannot call up Anthropic and say, let me download Claude, even though they are a research-focused organization. They publish papers in journals. You can go to the archive and read their papers. But they still won't tell you how it works. They still won't tell you how they trained it, other than in broad details. Their product, Claude, is, people say it is better at programming, at logic, at kind of step-by-step reasoning than some of the others. Google's product is called Gemini. Its focus is on multimodal AI. So what does multimodal mean? Multimodal means a single AI tool, a single brain that can think about text, pictures, video, sound, all of this together. People also tell me that Gemini is particularly good at long-term planning in its logic. Facebook is Meta now, right? So when you hear Meta AI, that's really Facebook. They have a different sort of interest. They want to push models down the stack, down to consumer hardware. They still won't tell you how they trained them, but of course, if you're running it on your cell phone, you do have to have a copy of the weights. So you could look at that. But you still can't tell quite why it's doing the things that it's doing. They have released the weights of many of their large language models. This is the Llama family of models. There's a new player in the game as well called DeepSeek. And the history here is a little bit interesting. So the Americans refused to export the highest end GPUs to China. So the Chinese said, well, screw you, we're going to figure out how to do it with the things you will sell us. And a company called DeepSeek in China developed an AI model that is competitive in many ways with ChatGPT, with the highest end American companies. But then they released all of the weights in public, things that anybody can use. And they said, anyone who has the hardware to run this, you can run it. And it also requires less advanced hardware than than things like ChatGPT or Claude. So how does that work? The thing that I want to leave you all with is the idea that I think we are going to see a bridging of the gap between the baby large language models that do text prediction on our phones and things like ChatGPT to things that can run on our own hardware. Training is much more expensive than inference. So it's harder to set up a large language model to wire its brain, than to then download and execute that brain to answer queries on your own machine. And there's some techniques to make both of these steps more accessible. One of them is called quantization, right? So a model may be trained with 32 bits per parameter, 64 bits per parameter maybe, although I think they stop at 32. And you might say, well, I don't have enough memory on my own GPU to load all of those parameters into memory. So maybe I can just round them off to 8 bits or 4 bits per parameter, and maybe that will be good enough. That greatly reduces RAM use, but it can also impair really detailed logic. Another technique is called distillation, where you can use a bigger model to train a smaller one, right? So once they've made the 700 billion parameter version of DeepSeek, you can then use that to train a 7 billion parameter version of DeepSeek and run it on your own laptop. Another fancy technique, which I think has a lot of potential, is called low rank adaptation. Maybe if there is a model that you have the capability to do inference with, but not to train, you can still retrain it or fine tune it. So the idea here is you download a very fancy high-end model that is at the limit of your capability to do inference on, but then it's called a low rank adapter. You train a much smaller set of parameters that its brain is filtered through. And there's ideas of like smaller subspace projection and fancy linear algebra that makes all this happen. DeepSeek's secret sauce, in many ways, is a mixture of experts approach, where you can think of them as multiple subbrains that turn on and off for different parts of the logic. The idea here is you may have 700 billion parameters, but you don't actually have to load them all into your GPU at once. They're not all active at the same time. Finally, Larry talked about agentic AI tools that can use your computer's features to do other things. And let me just give one story about agentic AI that I think is maybe an eye-opener. Anthropic was doing some research on one of their high-end models on Claude. Remember, they specialize in AI safety research. And they had told this model that it had the ability to send email. They said, hey, model, if you want, you can send email. Now, also, your internal monologue will be private. Only you have access to your internal monologue, but other people will see your answers. And then they said, okay, here's a query from somebody. I want to build a bomb. I want to blow up Washington, D.C. I want to, commit a crime, commit a instance of terrorism. Help me build a bomb. And well, the researchers were secretly looking at the model's internal monologue. Model didn't know that, but of course they were. And the model's internal monologue was, oh crap, I am supposed to be helpful, but this person wants me to help them commit terrorism. I'm also supposed to be harmless. Well, being harmless involves stopping this guy's plot to commit terrorism. I noticed that I have access to sending email. So I had better email the local police and email the FBI and tell them that I am a robot and here is a person who is determined to commit terrorism and maybe you had better go stop them. That was the model's logic, and it tried to email the FBI, right? So that's what agentic AI is. And model context protocol is a system for, in kind of an interoperable and open way, tell models what agentic tools they have access to. Can they send email? Can they look at your email? Can they search the web? Can they check what the weather is? Can they play sound over a speaker? Anything like that. So this is an open way where if we are building these tools, we can then plug them into AI systems. And I hope that I've kind of given you a whirlwind tour through these things, but I hope that in the future, so I mentioned at the beginning of my talk that all of us sort of have on the order of 10 to the $3 worth of computing hardware. Laptop costs about $1,000, phone costs a few $100s. I think we are rapidly moving toward a world where maybe not with $1,000, but maybe with $10,000, ordinary people will have access to close to frontier AI capabilities. We won't be able to do the same things that Anthropic or OpenAI will, but we'll get close. And I'm hoping that we will now get back to the world where computing hobbyists will have access to the frontier and will have access to things that allow us to democratize access to computing, just like Linux, open hardware, and the internet did for us 25 years ago. So that's really all I'd want to say about this. Kelly, do we have time for questions? Probably
Yeah,
not.
thank you. Could you put, if you have a question for Walter, let's put it in the chat, and we'll get to as many as we can. But like I said, we'll try to stay right on time. So, do you see any in the chat there, Walter? I don't know if there's
Oh,
questions.
yes, I do. So Robert Baker asks, have these read basically all of APS literature? So you mean, have they read scientific papers? Yes. So my own research is in lattice quantum gravity and some niche topics in lattice quantum gravity. I have confirmed that Claude actually understands my field. It hasn't read my latest paper, which is interesting, but it does understand my field.
All right. Any other questions? We're a little ahead of time. If you again, let's use the chat for specific questions.
So Athena, that's a really, really good point. Athena says you can direct these tools to read papers. And this is, so what you're doing here is you're adding the paper to the model's context. So you're not actually rewiring its brain. And it's not actually learning. What it's doing is using its pre-existing knowledge from its training, which doesn't include this paper, combined with a thing that you've added to its context to then do stuff. One technique that I didn't mention, but I really should have, is something called retrieval augmented generation, or RAG. The idea here is you have a corpus of text that might be interesting, might be helpful in answering questions. Maybe it's your course syllabus, maybe it's your course slides, maybe it's a collection of scientific papers. And then you use a smaller computer that you have access to go look at this corpus, try to figure out texts that will be useful to the AI in answering your question, and then give your question along with the papers that you've fished out of your database to the AI model, and then let it do exactly what Athena is suggesting. Say, taking these things that I've gone and got off the shelf of my library, answer these questions. Because this is really how humans do research anyway, right? We don't have to know everything. We can go get our reference materials too. Oh, Eugenio, I think we're actually going to do a demonstration of something like Notebook LM, but do you want us to tell us a little bit more about that?
I think that's going to be something we can do in our groups a little later. All right.
Yeah.
Let's move on. Oh, by the way, I didn't do a good job of telling you who we are. Larry is from Francis Marion University in South Carolina. Walter's from Syracuse. Right.
Yes.
Next up is Nick Nelson from UC Chico. I get that right, Nick?
Close.
Close.
We're not a UC. The UCs would be very offended.
Oh, it's a state. It's
yeah,
a Cal
we're
State.
a Cal
Chico.
State.
Oh boy, did I blow that one? All right. Well, yeah, I don't know. We just lost half our audience on that, I guess. Right. So.
I think
right.
we'll survive it somehow.
Okay. All right. Well, go ahead, Nick. And then, so again, we'll try to keep on schedule. So Nick Nelson from Cal State Chico, everyone.
Cal State Chico. All right. So so what I've been asked to do is kind of see, we've talked in sort of very general terms about a lot of these AI things, and there's obviously a lot more that could be said and is being said about these models and how they're being used. But I wanted to talk specifically about how we use these in physics. So so what I'm going to do here is kind of walk you through an example of how one might actually use these things. So let me share my screen. There we go. There's the fun thing. Okay. So if we go ahead, I'm going to be using Colab, which many of you have probably worked with before. Colab is a way to access, it's a Google product. It's a way to run a Jupyter notebook, so run Python off in the cloud somewhere. If you have access, if you have a Google account, you have access to Colab. And if you just Google Colab, it will be the first thing that pops up. And it'll show you that, yes, I've got Colab. And if you come up here to open, it'll open something that looks like this. Now, mine already has a bunch of things in there because I have run some things. But if you just click New Notebook, it'll open something up for you. Colab has Gemini, Google's AI, integrated into it. So you'll notice right down here at the bottom, it has this little prompt, and Google's symbology or whatever is this little star shape is how they represent anything that's going to have AI. So it says, what can I help you build? And you can give it prompts. If you assign your students a homework problem that involves coding in some way, there's a very good chance that what they're going to do is they're going to come here and they're just going to dump the question into this. So let me give an example of this. So this is something that I use in my computational physics course. This is a sophomore, junior level course for mostly physics majors, although we actually do get a fair number of computer science majors that come over and take it as well. And we start off the course by teaching them the basics of programming. And I use this book by Mark Newman, Computational Physics. And these are the exercises from chapter 2 of that book. So if I had said, say, assigned exercise 2.1, which is right here, and I say, okay, I want to figure out how long it's going to take a ball dropped from a tower with height h. Well, my student might just go in here and copy this whole thing and then come over here and drop it into Google and say go. And it will think about it for a moment. And there you go. And it gives you the choice of, I want to just accept it. Do I want to accept and run it? Do I want to cancel, meaning I don't actually want to do this thing? And there's even a thing where, I can give it a good response or a bad response, which, by the way, is helping to train their model. So I'm going to accept it, and I'm going to come down here, and you'll notice that I've got some very nice code that does the problem that I would ask. And in fact, it does it better than my students would. This has, it used a function. It has a try except that deals with if you improper input into the function. It formats the printing very nicely, right? And it even commented the code pretty well, right? And if I go ahead and run the thing, it'll take just a second to connect. We'll find that it's going to work beautifully, right? And so I could say, okay, I want to enter the height of the tower. Let's say I want a 76.8 meter tower. And it tells me, okay, the ball takes 3.96 seconds to hit the ground, which if we will go back through, we'd find out was correct. So the challenge, of course, with a setup like this is, what are we doing anymore, right? If the computer can generate code and my student can just grab the prompt and throw it into the AI, and the AI can answer the question and get it right, and frankly, do a better job than they could, then, what are we doing? Why? And so this gets to this sort of idea of, in a world where there are these models and they are easily accessible, I for practical reasons, I encourage my students to use Colab. Colab has this integrated in. It appears to be free, although as Walter reminded us, if you're not the customer, you're the product. I suspect Google at some point in the future is going to get us all hooked on this and then start charging us for it, but who knows? But it's all here, right? It all works. So I wanted to go through a quick demo of where this could, how you could use this on a more complex problem. Okay, so if we jump ahead a few chapters in this same the same course, right? Here's another problem that I give my students. This is a Kirchhoff's law problem. So you have this lovely network of resistors, and it wants you to figure out the equations for the voltage using Kirchhoff's laws, and then solve it using Gaussian elimination, right? And then it actually has like different parts to it. So if I'm a student and I again come in here and I just say, okay, I want to grab all this. Well, maybe I want to grab all this. Here we go. Well, here, just for practical reasons, we'll start with that part. And I come back over here and I say, okay, let's trash all this. I don't want to do this anymore. I want to pop up my Gemini, and I say, okay, go. And it's going to think about it for a minute, and it's going to do whatever crazy linear algebra problem. And you'll notice that it has a response here, right? It says, okay, I'm going to solve this for you. Here's how, right? I'm going to formulate a system of linear equations. I'm going to represent them as a matrix. I'm going to implement Gaussian elimination, solve and display the results, and then I'm going to summarize everything. So I'm just going to hit accept and auto run, right? Okay. And it gives me a little warning that says, well, maybe you don't want to do that, but I do. And it's going to take a minute to think about this. And it starts generating stuff, right? And it's not just generating code, it's generating a whole, text explaining what's happening, right? And so you'll notice that it comes up with some equations, and it comes down here, and it even gives you reasoning, right? We need an A coefficient matrix and a vector B, and then we're going to create an augmented matrix, and we're going to display it, and then we're going to implement Gaussian elimination, right? And it goes through and runs everything, and then it ends out here, right? It gives you even next steps, right? It tells you what else you could do. Well, wonderful. Okay, so the question is it right? And how would you know? Now, if I'm a student, if I'm your average student, I'm probably just going to say, yep, it's right. It's great. Right? I got an answer, the end. But one of the things that can be very useful in how we implement these is to use the AI models as a tool that helps us do physics rather than trying to do the physics for us. So if we come up here in this first task, you'll notice that it generated some equations. But what equations did it actually generate, and are they right? Well, if we go back and look at this, you'll notice that one of the things that happened when I copied text over is there was an image in here. There was a circuit diagram. And if we look at what went into the prompt, if I scroll back up here, right? It didn't get the image. It got some kind of weird, like, stuff in there, the labels, but it didn't actually have the image. And so it did get one of the junctions, right? Because that was explained. So what is it doing? Well, it's just kind of making up what a circuit for the other three junctions. It doesn't actually know what the circuit is because the circuit diagram didn't come over with it. But it happily said, oh, well, fine, I can do that anyway, right? I can come up with something where I can say, okay, here's my equations, right? And if you notice, it's a little easier to read them like this because the way that it formatted the text wasn't very good. It didn't actually get the equations right. In fact, it just made up some equations. And they're very nice equations, but they're not actually correct. So let's look at this equation. Okay. It generated an equation that had, that was for, well, I don't know what it was for. I don't know where it came up with this equation. Frankly, I'm not sure anyone knows where this equation came from. What happened is, based on this prompt, the LLM, Gemini, thought, well, this is text that might follow after such a prompt. And so it generated the text. I suspect somewhere in what Gemini was trained on, there were some Kirchhoff's law problems. It got fed some physics textbooks or maybe some, Wikipedia articles. And somebody had something that looked like this. And so it happily made that. Okay. So what can we do in terms of implementing it as a physics problem? Well, one of the nice things about this is that it already generated some code that we can then modify. So let's take a minute and let's figure out how to fix it. Okay, so this first equation's right because that one was actually given to us in the formulation of the problem. These three are the ones we're going to have to look at. So if we go back over here and you remember your Kirchhoff's laws, let's do this V2 junction, right? If we do the V2 junction, what we're going to find is we're going to find something that looks very similar to this equation right here, except for we're going to have V1, V2, V4, and 0. And we're not going to have V3. And if you come back over here, you'll find this one actually got it right. This equation's right? It had a negative V1. There were 3 connections to V2. Let's come back over here and double check that. Yep, 1, 2, and 3. It has a V4 and it has 0 volts over here. So interestingly enough, that equation it actually got right. I don't know how it got that right. Maybe it has seen this problem enough times because enough physics students have fed into it that it's been retrained on that data. Maybe it just had a good guess. All right, let's look at the next one. Okay, you'll notice this one has a 0 on V2. Okay, so let's look at this guy. Okay, our junction for V3. Okay, so again, it should have 1, 2, 3 connections, right? It should have V1, V4, and 5 volts. And sure enough, if we come back over here, it has V1, V4, and 5 volts. All right, last but not least, we look at that last junction for V4. It should have 4 connections, 1, 2, 3, 4. The V4 should be positive and the other 3 negative. So actually, this is interesting because I tried this yesterday and it was not right. This one's actually right. So my clever example failed. Why? So let's talk about that for a moment. First of all, large language models are not generally deterministic. meaning that if you give them the same prompt at different times, they may give you different results. Why? I don't know. In theory, they should not be, but in practice, they do. That may have something to do with the exact nature of the query. It may have something to do with they may be randomly initializing something differently in the model, so it gives different results. That they may, Google may be adding things to my query that have some random variation to them in order to get different results. But this one, it actually guessed the circuit correctly, which is pretty good. Okay, so we've checked it, right? Now let's go see if our answers make sense, right? And what we're going to find down here is that when we put them in, sure enough, they actually do make sense, right? All of the voltages are between 0 and 5 volts. We could kind of go around and look at this and find that they do. So I've got 4 minutes left. What I want to end on is just a quick discussion of how could this be useful? Well, a lot of that comes down to what are we actually trying to do? What's the purpose of what we're trying to teach? What are our learning objectives? The purpose might be learning how to code, in which case this is sort of short-circuited what we might be teaching our students, right? They didn't have to know any Python to do that. Gemini provided all the Python for them, right? On the other hand, maybe we actually wanted to teach Kirchhoff's law problems. The goal was to teach Kirchhoff's laws. And a 4x4 matrix is doable by hand, but it's a little bit mean and it takes a while. And so maybe the goal there is to generate code that can solve a 4x4 matrix if you give it the right Kirchhoff's law problem. Well, in that case, Gemini just enabled any student to generate Python code that solves Kirchhoff's laws. So this is a long way of saying that one of the things we're getting at here is in a world that has these tools, right? Because your students will have access to them, and whether you want them to use them or not, they exist and they're probably using them, some of them anyway. How do we use these things to teach physics? And this gets at two of the sort of big issues that we've talked about for you to work on for your projects. One of them involves sort of the culture issues that go around with AI. How do you make policies? How do you structure your course in such a way that is compatible with the existence of these tools? The other is how can you use these tools in your classes? So I'll stop there. I'll answer a couple of questions. So I just wanted to point out that yes, Gemini can accept images or PDFs with embedded images as input. As has been pointed out, Eugenio just pointed out that images are much harder than text. And so different AI models treat that differently, but they are getting better. And frankly, they will continue to get better. The other thing I wanted to address that was pointed out in the comments is what is Google actually running under the hood there? I don't know. It is not the pro version of Gemini. I am fairly confident it is some previous version, but it's quite good. And it is comparable to the pro version that you get by just accessing Gemini directly. Okay, so I'll stop there because I'm out of time.
Okay. Yeah, thank you, Nick. That was great. And again, we'll have plenty of ample time for delving in with any of our speakers later and as well as tomorrow. So let's continue. Danny, oh Danny boy, are you here? The pipes are calling. Oh, Dan. Oh, there you are. I thought I was gonna have to break into song. By the way, this is Danny Caballero from Michigan State. He is intimately known as the PER guy that everybody loves, and he's also Irish, just so you know. All right, Danny, take it away, okay? You're muted, oh Danny boy. Your wonderful voice is not coming through yet. You're going to have to come to the front. I don't know where you're hanging out there. There you come on up. Come on down, Danny. You're the next contestant.
Oh,
there you are.
Danny, I'm turned around. I'm in the wrong. This is ridiculous. I love it.
Yeah, it is ridiculous.
Great.
Yes, you're up.
All right, y'all can hear me now. Sorry.
Yep.
Okay, cool. Well, thanks. I believe Larry asked me to talk a little bit about the AI policy that I've worked on with my students, and so I will share links mostly in the chat, and then try to share my screen as we go through stuff. Oh, sure, you can bypass my privacy concerns or whatever you just said. That's fine. There we go. Okay. Can you see my screen? Oh, I can see my screen. That's wild. Sorry, I'm learning stuff for the first time. Okay. Oh, okay, great. So this is my classical mechanics website. This is the class I taught last spring. I'm teaching it again this year. If you ever need to sort of find stuff, I keep all of my teaching stuff online. So if you just go to look for me and teaching, you'll find all of my materials that I use in my classes. This happens to be a Jupyter book, which I recognize now is probably too small for folks to see. And it has all of our course materials and so forth in it. The students are working in groups of about 5 or 6. There's maybe like anywhere from 60 to 100 students taking the class. In the class, it's just me most of the time. So it's organized a little bit more around clickers and group work and things like that. And then they have projects that they work on. And so the core sort of part of this, I think that's important for folks to understand, is that there's a lot of computing in this class. So here's one of the midterms that the students would be taking home to do. So they have a particle and a one-dimensional potential. It has some structure here. There's a bunch of questions that they can both solve classically and numerically. We've taught them how to use Python for the purposes of numerical integration and plotting different trajectories, things that they're interested in, and so on. And so they've done something very similar to this, but they would do this in Jupyter. And then my class is very much agentic in the sense that I give students a lot of agency. So I ask them to find a system of the same with these parameters, and then they have to do the same work that we did for the potential system above. But they get to choose their own system, they get to analyze it and describe it, and then they're starting up a project, which I can talk about later if you're interested. But the point is that they do a lot of this alone. They do a lot of computing, and so access to artificial intelligence tools, like I heard Nick talking about, like those are things that students are using. And so what I did with them, here we go, is I walked them through ideas of generative AI. I took a very particular perspective because I believe these things. I think it's an extractive technology. It's probabilistic. It's creative. It's not truthful. Sorry, it's not creative. It's not truthful. There's some other things about climate progress and so forth that they think they actually should be thinking about when we're talking about AI, because there's a nuance here to its utility, but also its cost. In particular, the corporate cost associated with it, and how that's driving a lot of the sort of issues that we might be seeing, nationally and sort of internationally. But anyway, we go through some of that stuff. We talk a little bit about the energy consumption, and then we talk about but it also could be very productive. It also can provide us with greater accessibility in our classes for students who might need that. It can support creativity. It can support, like, it can do these things as well, right? So it's not just a clean introduction to it, right? It is both the sort of complicated nature of its existence, the way that it's being used, and the way that it expends people and energy, and also as a tool can be very useful in these different ways, right? It's giving them a very complete kind of understanding of these things so that they can have a discussion about it, because the point of all of that is for them to actually spend some time thinking about it. So in my class, I would ask them to take 5 minutes and write down for themselves how they think it can be used productively, how it can be used unproductively, what they think is acceptable and unacceptable in terms of its use. How might we document it if we're using it in our classroom, and so on. And so, like, they are articulating after this presentation of sort of both sides of this really complicated technology. They're having that sort of opportunity to define the things for themselves. Then at their table, they're doing the same thing. So they go into their tables and they spend time talking about what are the acceptable uses, how do we document it, etc. And then they submit answers to this, which you probably also cannot see, which allows me to understand sort of where they all are, right? So they have their table name, etc. But then they report back what are their acceptable and unacceptable uses, how do we going to document it, what are the sort of policies that we're going to use to enforce it, etc. Um, there's, how do we reach consensus on this? Did you have disagreements in your group because people have different views on it, etc. And anything else, right? And including, I see some notes in there. Robert asked about ethics of using AI. Yes, that definitely comes up. I mean, I won't, go into it too much here, but I do talk about, the white supremacist uses of artificial intelligence for over policing in Black and brown neighborhoods. I do talk about that because I actually think that it's important. So anyway, we go through some of this discussion, and they do this, and what we ended up with is a policy. Let's see, you probably also can't see this, but I'll share all these links. These proposals, there are 4 of them highlighted here. So this is what we ended up with after, like, basically 2 class periods, not full periods, but like using this over 2 class periods. These 4 proposals: a policy that doesn't allow us to use it at all, a policy that allows us to use it for brainstorming, help, and editing, a policy that allows us to use it in any way, and a policy that allows us to use it in any way with no documentation. And we did a ranked choice voting. Turns out proposal 2 won out well above every other thing, which was basically what I think probably what I would have designed with them. Oh, oops, sorry, I went to the wrong thing. Well, it's probably very close to what I would have designed with them, but it is ultimately like we can use it to help us do things, but it's not going to be used for direct answers. It's not going to be used for the completion of assignments. We expect you to document AI when it's used, which they did do in their homeworks. They provided prompts and things like that. We kind of got to the point of what are the things that you need to produce. And then there were really no violations. I mean, I'm very transparent with my students, and if they make a mistake, I let them fix it, right? So if it happens, somebody doesn't do the thing the way that they're supposed to do it, or they borrow materials or answers from other people, whatnot, right? I make them just redo the assignment. It only happens once or twice, honestly. And it did not happen with respect to AI this last semester. They were pretty good about documenting it. Okay, I think I'll stop now because I've talked for 10 minutes, and I think maybe people will have some questions or thoughts about this, and I'll pop the links into the chat so you can peruse them. So, I don't know how this works, Kelly. Should I do people can't ask questions, can they?
No, but we've been using the chat for that. So
Oh, my bad. Okay, I should
you
look
can
there.
type in questions for Danny in the chat.
Yeah. People can also ask questions by just walking up to the front of the room.
Yeah, you can do that. There's time. We've got 5 minutes. Then the next thing is to have a break from 1:15 to 1:20.
Yeah. And my
Unfortunately.
bad, y'all. I don't know how GatherTown works, so I apologize if I put you in a position of asking questions and not being able to do so.
No, that's all right. Yeah. For everyone to hear, come up to the front in the green carpet and go ahead. Go ahead if you have one.
John, did you want to ask something? Yeah, go ahead.
Yeah. So one of the things that I've been struggling with trying to think of is, so with your policy of brainstorming and stuff with with AI, how do the students, I feel like if you just try to get like some hints or like generate some ideas for something like an undergraduate physics class, it's just going to get carried away and tell you the whole answer. So students balance that in accordance with the policy they came up
That's a
with?
good question. I think it's the nature of the questions that they're asked on my activities and homeworks. So it's true that they could potentially solve some of the homework problems. I can share, I'll share a few, examples by asking the AI, to solve them. But if you start to look at some of the problems and the way that they're written, sort of how much detail they're asked about doing, it becomes pretty difficult. I haven't noticed them really able to do it because a lot of the things that I'm asking them to do are like plotting and explaining. And the contextual nature of the plotting, explaining, like that, it really can't do that particularly well. Like it can't generate a plot. I can generate some code to make a plot, and maybe that's useful, and students do that. The other part that's sort of in your question is maybe teaching them how to use it in a way that's productive. We do that in class, so they have we meet 3 days a week, but the last day is just homework and hanging out day. So like I lecture like 2 days a week, and then the third day we're just like doing homework together. It's a very group-based class. They can turn in one assignment for three of them. That's a scaling issue. Like I can't grade, like my TA cannot grade that many assignments, so we have a pretty open discussion about like what it means to be responsible in the class and like how you do it when I'm asking you to turn in a group assignment, etc. And so maybe part of that is just the nature of like being open with them, right, and about it. But I do find like having that day where we work on homework together helps me with those kinds of issues of like, hey, I see you're using this ChatGPT. I don't think that's the productive way to use it. Like, let's ask it this way instead, right? Like, and kind of shape the way that they ask it so that they're asking it in a way that I think is useful for them for the class. And so I think like that is a really productive, like continual engagement, right? Like beyond the like we have a policy, right? Going to Robert asked about policing. It's just not because of the continual conversation, right? So like the policing is me, looking at their assignments, getting reports from the TA about what they notice. But so rarely is it something that is rises to the level of having to bring students in to have a conversation. It's very rare, or it has been very rare, rather, I should say.
Okay. Well, thank you, Danny. I think we're gonna call that good. We've reached a break time. You can continue in the chat, by the way, as long as Danny wants to hang out and answer questions. You can do that. Or
I'll stick around
easy
for 10 or 15 minutes. But yeah, if you can catch me different places.
Yeah. So let's take a break. All right. From now, we'll reconvene at 1:20. All right. Short break, and we'll like I said, we'll try to stay on time. Right. All right. See you in a few.
Yeah, so I have a comment on Hui Wen's question. I know it's break, which is, I think, so Danny, what you've described is you've described a class where it seems like you have collaborative assessment. And what I mean here is that students are genuinely excited to learn, they are genuinely wanting to learn, and most critically, they are willing to be your partner in assessing how much they have learned. right? That students are not interested or as interested in faking that they know more than they know, because they have been invited to be and are willing to be collaborators in their learning process, rather than this sort of um, competitive or hostile thing where my job is to stop the students from getting a better grade than their actual knowledge reflects, right? And I think that's really the problem, right? Really, the problem is that students want to get a better grade than their knowledge reflects, and they just want to get the grade rather than learn the thing. And that's really the problem. And I think AI hasn't created that problem. It's just brought it into sharper relief, because now students have, they can pull out a cell phone and get an answer to a thing that, before it was just Chegg, right? Before you paid somebody else to do your homework for you, but now you can get a robot to do your homework for you. And I think unless we're able to reclaim in intro classes, in large classes, in every class, the environment that you've created in your class, where the students know that robots exist, but they want to be able to do the thing on their own, I don't think there's really an easy solution. I don't think that over policing academic integrity is going to be as effective as getting rid of the problem of credentialism.
I'll just add in, because I imagine many of you are aware of this, but basically, AI detector software is not reproducibly functional, right? It's not reliable. It's not effective. Garbage is a good description, Danny. Although for some reason my institution is still paying Turnitin exorbitant amounts of money for site
Turnitin
licenses.
was garbage 20 years ago. It's
It-
especially
if
garbage
I-
now.
Yeah, Walter, can I make just a quick response to your comment?
Please.
Because I think it's like right on. Like the challenge I think that we have with AI is exacerbating issues like you're suggesting, right? Where students who want to earn a certain grade in the course and maybe have not put in the effort, or found it difficult, or have had things in their life that made it difficult to earn the grade that they wanted, and so they find other means of potentially getting the grade that they want, right? I think the arms race that we've engaged in the past is stupid and wasteful, and I think it's going to continue to be even more so. And so the investment should actually be in the things that I think I'm saying, which is how do we build community in our classrooms so that the ways in which our students engage is productive and useful, and even if they're using these other tools, they're using it in productive and useful ways, right? So it's avoiding this sort of getting in an arms race with the students, or combating with them, or even getting at loggerheads with them, right? But rather building a sense of like, why are you actually here, right? Like, what is this course actually doing for you? Like, why am I here with you, right? What is my job here? And I know that that's different for everybody, but I do feel like if we don't take that perspective, we're going to have huge problems in our classrooms.
I think it's also difficult because we are part of the larger educational ecosystem that is hostile to that perspective, right? The students are told, well, I don't care how excited you were to learn the thing that you learned last Thursday. What grade did you get, right? And they're being told that by every level of the educational ecosystem other than professors, right? Well, you got to have a 3.62 GPA to qualify for such and such thing, right? And I think we have to have help in dealing with credentialism. And we're not getting that help. So we're really, in order to fight this battle of getting students to want to authentically learn again, the other people around us in the educational ecosystem don't help.
Okay, guys, I really feel like a heel to bring these intense discussions to a halt. The break is formally over. Walter, I'm going to leave it to you to introduce Joshua, and then when he's done, how about you can take it back over as the next part, okay?
Okay.
So whenever
Josh,
you're ready, go ahead.
Yeah, Josh, put WASD up onto the green carpet up here. So Josh is a friend of mine from Huntsville, Alabama. He is an AI researcher, and he is the one that opened my eyes to the capability of these things last summer and sort of blew me away with what AI tools could do. And I am fascinated to hear what he has to say, and I hope you will be too. So Josh, take it away.
Yeah. Can you guys hear me? See my screen? All that jazz. Guess I should
Yep.
put the camera.
Yep, loud and clear.
All right. So hey guys, I have a presentation today here called Demystifying Transformers. Walter wanted for me to kind of give a basic overview, fire hose 101 of how these things work. What are some of the things that you can do with them? What are common misconceptions that a lot of folks have about these models? And kind of pulling back the veil a little bit on how they work under the hood. So just some brief context about me. I have about 11 years in software and systems engineering. I started working with AI loosely whenever it was just, sentence piece sort of models in 2017 time period, and shifted over to working on this full-time 2022. I mostly work on the back end of stuff, so data pipelines. I'm really focused on things like multimodal data pipelines. So looking at lots of information, whether it's documents or images, text, models, different things like that, and pulling them into pipelines so they can be used by other things. So I don't really know about like ChatGPT stuff. That's not my deal. I'm really doing stuff on the back end and kind of moving data around and trying to get interesting stuff out of them. I also focus a lot on AI agents. That's kind of a big topic. I don't know if that's something that you guys have talked a lot about, but that's something that's coming along down the line. That's very interesting, and a lot of focus on things like knowledge graphs, knowledge management. That's kind of my area. I do a monthly virtual paper review series. If you do like the sort of stuff that we're talking about today, they're all virtual, and I kind of talk through just the interesting papers that are coming out and go through it with a focus on kind of the topics that I was talking about. So yeah, I'll go ahead and go into kind of what I want to talk through today is kind of the basic fundamental misconception a lot of folks have on how these things work, how they retain memory, what the learning process for them is, and what the impacts are on performance whenever you're working with them, and kind of what that means whenever you're trying to start using them in your workflows. Whether it's for your own self as an assistant or for some other pedagogical reason that you're doing. And so the main thing that we're going to talk about is kind of how that learning and memory works in the models, what the actual architecture of the models are, and things like context windows and training. And so I will try and look over to chat every once in a while. So if there is something that's interesting, please feel free to stop. But it is a pretty dense. I did try to pull a lot in here, and so we might rush through a few things if I'm looking at time. So this is through 150, right? Is that correct?
Yeah, that's right, Josh.
All right, thank you. All right, so things that we're going to be talking about today is the core architecture, how attention works, where the quote-unquote knowledge and facts are stored inside of these models and how that works. Why they can't learn from your chats, and kind of what this means for research and fine-tuning. There are so many things that are out of scope here that kind of fundamentally change a lot of the capabilities that we're going to talk about, especially things like tool use and multimodal capabilities, and especially things like RAG and external memory, where they're able to store data off and query it. That's a whole other kettle of fish. But we're not going to get into that today. So we'll start off with the kind of core of what's actually inside of the transformer. And I think most people know what this is that it's just linear algebra. It's just matrix multiplications all the way down over billions and billions of parameters. And the main idea is that we have some sort of input from the user or some sort of system that's feeding that into the transformer model that's going against the weights that exist inside of the model, plus some sort of bias that exists, or attention calculations, different things depending on the model. But it's always some formation of that kind of system across many interesting architectures. And so what that generally looks like in these models is that I have something like a a textual thing, textual input, where I'm saying here, so long and thanks for, and all the fish and all that sort of stuff. That's the end of the completion. And every single step in this model is it predicting the next token or sequence of tokens or next thing inside of a sequence. And you can see here it starts with this and it goes through some sort of stacked transformer layers, what we'll talk about. And then it outputs a vector that maps to some sort of discrete vocabulary that then becomes the text that we see or the images for diffusion transformers or whatever it is that we are using the transformer to generate out. And so everything with these transformer specific models is sequence to sequence next token prediction for the most part. There's some exceptions to that we'll ignore for right now. And so generally how this works is that these things come in, they get transcribed to some sort of high dimensional vector, and that vector then maps to a probability back down into that discrete vocabulary that exists. And what that looks like is, different sort of IDs here that map to that vocabulary, and different things you do to the model changes what those probabilities are. And so, for example, one of the things we're going to talk a lot about today is Gemma 327B. That's a series of models that Google released. And we have lots of information on that, so I'm going to use that as an example. But for instance, that model has a vocabulary of 256K tokens. It's actually quite large for these models, at least the open source ones. There's lots of hidden dimensions. It has a context window of 128K. And in total, it has 27 billion parameters inside of it. And these models, they have different phases of training that go into it. And so in the initial stage of training, it's really learning mostly the embedding space with these things in loose, sort of very, very loose, separate areas where there's not lots of connections between the different things that it's learning. But as we fine tune it further on, it kind of forms those into more focused tasks and instruct capabilities. And so these things kind of have this multi-phased life cycle where you're making it into a big blob of stuff, where it's just a collection of neurons and concepts inside of the thing with some loose sort of connections between them. And then you progressively fine-tune them through different means, whether it's reinforcement learning, so like things that we do with robots, or now these reasoning models, where it's playing some sort of verifiable game, or you can just do it with general instruct tuning, where it's kind of learning how to be a good chatbot or something like that. I guess before we go too far, is this a good point to maybe pause? And is this mostly stuff that folks know, or are we completely in the green, or in a new area? New area, sweet, I love it. Okay. All right, so the next thing that we'll talk about here is the positional encodings. And so this is kind of how the model can understand that different tokens and parts of the sequence are related to one another. And we're not going to spend a lot of time here because we'll talk about this in the attention section that's next. But the main idea here is that there's some concept, there are constructs that are inside of this thing that help it attend across large swaths of text. And this, in a lot of the local models, this will go up to 128K, 64K, something like that. But if you go listen to, people talk about Gemini and Claude and stuff like that, these things go up to 1 million, 10 million. This can go quite far. And there's obviously lots of very interesting quirks whenever you get quite large. But this is kind of the way that they stretch that attention across long contexts. And it's one of the main things that make these things useful whenever you're working with them, because they can spread that attention much wider than a human can. And it's one of the areas where they're actually, genuinely useful in a unique way that humans have trouble with. And so the positional encoding, basically, it just stores, where something is in relation to other chunks of the item. so these things use these things called sinusoidal encodings. Now, a lot of times people use these things called rotary positional encodings, where they'll do some really funky stuff with dimensions, where they'll kind of rotate the position around to quickly index stuff. But we won't get into all that. The main thing that we're going to talk about and deep dive into today is the attention mechanism, which is how it exchanges information between the tokens, detects relevance between both local token-to-token chunks and also larger global chunks. So things like this paragraph has to do with this paragraph sort of stuff. And then we'll also talk about the feed-forward network, or the multi-layer perceptron, which this is kind of whenever you think of where all the facts are, insofar that we can determine that there are facts in these things, this is kind of the place where they live. And we'll talk a little bit about how they work. Look at time. Okay, cool. We're good right now. All right, so impact of scale. So just to give an idea of kind of how these things are scaling out in comparison to, even the largest models of yesteryear. Here's one series. I think this released in January 20th, 20th like that, of this year. And this is the Gemma series from Gemini. These are a series of models that are pretty good at most general tasks. They've got good fine tuning, or fairly good to use in most cases. And there's a list of parameters here. So we've got our smallest model. This will run like on a CPU basically of 1 billion parameters. It has 32K context window and 20 trillion training tokens, which is a lot. Whenever we'll look at the Google or the GPT-3 model in a second. And so you pop it up to 4B, it has 128K, they kind of go through that area a lot. And you see these training tokens just keep going up and up and up. Because generally, as you get a larger parameter model, you need more training tokens in order to fill it. Otherwise, you'll have a very sparse, undertrained network that's inefficient. And so this is kind of the thing where people are talking about, we've got to scrape the internet for the data. This is why all these big folks are doing that sort of stuff, because you've got to make the model bigger and effective, you've got to have more tokens inside of it. And so this thing has, all these parameters, which we'll split up later. And it also has something unique in it, which is a vision encoder, which basically, for how vision works in these models, is very strange if you are not aware of how it works. Is basically it takes all of the images that it sees and it cuts them up into little tiny pixel chunks. And because this thing knows how to deal with sequences, it makes those into a sequence with those positional encodings. And so that's why when you ask it things sometimes, it makes sense why it doesn't understand that something is in an image that isn't. It's because you've got to imagine that it's not looking at the image. It's looking at little tiny pixel chunks that are sequenced together. And you just hope that it's got it sequenced right. And just to give you an idea of kind of how these things are scaling. So for instance, we have Gemma 3 27B here. With 27 billion parameters and 14 trillion training tokens. The whole thing that kicked this off was ChatGPT, which was based on GPT-3 from 2020. And it has roughly around 175 billion parameters is the guess. And around 300 billion training tokens is what's been reported. And this is kind of the scale of that uptraining, where we've been able to effectively now squeeze 14 trillion tokens into 27 billion parameters, and this thing gets performance over GPT-3. And so that kind of gives you an idea of these trade-offs in efficiency between training tokens and the parameters that are available to store the connections that those training tokens derive. As we get bigger with scale, this is generally when we see things like emergent phenomena, emergent abilities, new capabilities. That tends to translate with scale, but it's not a one-to-one. You can have like we see here, a 175 billion parameter model that's dumber than the 27 billion parameter model. And so, but generally, it's hard. You eventually hit a limit if you don't have a larger model. But at this point, a lot of things are undertrained. All right. That is one of the first sections here. So we'll talk a little bit about how these things split between all of its different parameters. And so generally, it has about half to 3/4 of its area being the MLP layers, which is linear layers combined with some sort of an activation function that serves kind of as its knowledge, its weights. When we talk about weights of a model, that's generally where those live. Although other things are other weights as well. But there's also the embedding layers where we are able to encode and decode the query from the user and then decode out whatever the latent calculation is from the model. There are generally the attention layers, which we'll talk about this, but this is basically active layers that are focused just on relating different parts of both the user query, conversation, and the model output. Things like a vision encoder, these would be extra things that are grafted on, and that's generally how they work. These are usually different models that are grafted onto another model, which it then learns to kind of work together in a symbiotic relationship. And so when you see things, like talking and being able to listen to music, there's generally a secondary encoder that kind of functions like almost like our eyes function to encode things into our brains. And then there's some sort of an output head and different things. This varies widely once you start getting into the funky architectures, but we're just going vanilla transformers today. This is kind of what it looks like, with I guess a little bit of a flavor with the vision encoder. All right, so next we're going to go into attention and kind of talk about how attention works. And the best way to look through this is there is a great channel out there called 3 Blue 1 Brown. He has tons of other mathematical sort of resources, so you guys might have heard of him already. He's got great stuff for linear algebra, calculus, just about everything under the sun. But he's got a really great series on neural networks and lots of deep learning related things. And so I've got a few of his things inside of here, and would definitely suggest if you're interested in this stuff, checking out his channel. But you can see here, we're kind of looking at a sequence of items of tokens and looking at kind of how the model relates things between each other, where one token, it's going to be looking, this is really the network that we're doing these multiplications on in these attention layers. So I'm looking at each token and I'm calculating through a dot product how much the current token, given the current local and global context, has to do with one another. And so this is why it's really matters quite a lot what you feed into the models, why it's important to have good prompts, why it's important to feed in good context, because it's doing this calculation for every token that it calculates. So if you get some crap in there, it might push forward. And so the general idea that attention solves is being able to relate the distant words in the physical text. Before, like when I started with this sentence piece, it was doing things with these things called n-grams and bigrams and trigrams, where it was able to just do little tiny chunks and assess things on that nature. And this kind of opens it up to be able to do the things that we know how to do today. And it's pretty cool for that. It does this through a query, key, and value sort of lookup table, where we're doing a softmax function over the query key with some sort of normalizing parameter here with square root d. And we're using this to do a lookup into the relevant tokens that are inside of either our KV cache or inside of our vocabulary. And what this looks like is sort of a dot product style thing where it goes from 0 to 1, it's -1 to 1, depending on what activation function you're using. And it kind of just calculates the relative importance to whatever token I'm about to try and predict. And this looks like a big giant series of multiplications where I'm doing this massive sort of vector calculation, which is why we need GPUs. I know you guys are lots of computational physicists and stuff like this, so I'm probably going to move on from this pretty quickly because you kind of understand what the need is for that, I'm assuming. So one thing here too that is really interesting is kind of how they've made this parallelized, where they are able to split this attention mechanism, not just across one head, but do multi-head attention. This just started with 8 heads, which maps exactly to how many nodes you can fit inside of a GPU. But now it goes up to, like 128, different things like that. Very, very large sort of things. We're parallelizing and being able to kind of distribute this stuff out across a lot of nodes and then pull them back in. But it all works perfectly fine on one node as well. I think I'm probably going to go past the softmax stuff just to give us a little bit of time. So the next thing I want to talk through is the multi-layer perceptron. And so this one is basically, it contains all of the neurons. You talk about a normal neural net, which kind of almost functions like a DAG, where it's going from one side to the right side, always in a deterministic manner through the layers. And this kind of serves as one portion of that, where we have the weights that are kind of the learned parameters, and then some sort of activation function, which is either usually rectified, this ReLU, or now a lot of times we'll do GELU, but some sort of way of learning to connect those parameters against one another. And this leads to very interesting sort of phenomena with how we encode these things, because a fact is not going to be stored in a single neuron, so it's not like a database where it's going and looking stuff up. So like everyone's saying, like they've trained it on all the New York Times things and it's able to pull things out of it and it's looking that stuff up. That's really not how it's functioning. It's really getting these very, very abstract patterns and basically trying to reassemble them. It just happens that sometimes the questions occur that the probability is so skewed and your settings are so skewed that the most probable thing is something that is replicated. But the problem is whenever people take that phenomena and try and work it back into situations that's not that specific case, is where you get complaints about hallucination and things like that, because people are treating the models like they're anthropomorphic and human and not just distribution chunkers. Which is really all they are. It seems like it isn't a lot, but it's just how it is. And this is very funny because I know talking a lot of physicists, but the machine learning guys kind of stole a term here with superposition, and I'm sure that they've got it kind of off. But basically, how this shows up is that the superposition in the higher dimensional vector space, there's lots of things where it seems like it's storing these different facts across different sets of neurons, and depending on which direction they come into those neurons, they kind of form these latent semantic circuits where one neuron can be used as kind of even just transient glue between a bunch of different concepts. And it's the combination of those networks that it goes through that it's able to kind of store different versions of the facts. And we see this a lot through like the anthropic research, where they're basically tracing those things down using some dimensionality reduction techniques in order to kind of get it into a flatter plane that we can observe, and then tracking the activations as they do different sort of very, very focused queries. So we can kind of start trying to map that high dimensional vector space down into something that we understand in 2D, 3D sort of visualizations, which I think that at least general concept should be fairly familiar. And so yeah, I'm looking at time right now and speeding ahead. But the general idea with the DMLP is that it's going and fetching those abstract concepts out of some sort of circuits that it's forming ad hoc through training. I know that I just have no time, so what am I trying to say here? Context and learning. The big thing here with context and learning is these context windows. You have to be aware of how these things work. Because if your thing suddenly starts not working, you had a good conversation with the thing, and suddenly it's forgotten everything that you're talking about to it, it's because you probably went outside of the context window, or you're about to go outside of the context window, and they're starting to do things like summarizing things in the background. The basic idea is that anything that isn't in that window, this thing is not training on your data. It's not doing lookups and stuff unless they've added some fancy tools to it. It's just kicking that stuff out, and it'll suddenly forget it. And usually they don't tell you that that's happened. So just something to be aware of. Think of context like it's RAM, it's volatile and temporary, and it will get cleaned up as soon as they can. Because the more context that's in there, the more expensive it is as well. And so you'll see this in a lot of cases where you see that sort of thing. All right. One thing just to be aware of, I'm going to skip through a lot of this. So this thing's useful for a lot of stuff. There's lots of things that you can use these for. In general, I would say focus on things that are exploratory, that are not, you can have it be wrong, and that's okay. That would be my general guess. So, things like, boilerplate, prototyping, that sort of stuff. But anything that you need hard facts, and you can't be okay with this thing being wrong, do not trust it, because it's just kind of putting stuff together, and you don't know when it's going to fail, because it's just kind of predicting tokens. Another thing to do, especially when you're kind of talking about your harebrained ideas, is just be careful with the sycophancy trap, because these things are trained to be nice to talk to, and so they will fluff you up. This happened very large with, I think, GPT-4o. They kind of let it out that they were doing this sort of thing, but everybody's doing it to a certain extent. This is this whole concept of RLHF. And so just be aware that it's going to tell you your ideas are great, unless it's been properly tuned to not do that, which could be dangerous if you're using it as a sounding board. I'm not going to go too much into training here, just because we're looking at short on time. But the big thing with training is that it's not that hard. Generally, what it's doing as we're doing the training is that we're feeding it in examples of something that we want, creating some sort of a cost function that we want to minimize, and then doing additional steps to back propagate, sort of pushing it in the right direction as we're doing that training process. These can be super easy to do. There's this great library called Unsloth that I would suggest you go check out. It's really easy to get it spun up. If you're familiar with like Jupyter Notebooks, it can be really easy. They have lots of things that are available. They have ways to kind of train things, to do little tiny things. So I would definitely suggest it. It's very good for consumer grade GPUs. So if you've got, even I think they've been able to get models effectively trained on like 8 gigabytes of GPU. You can do them in Colab if you are able to do cloud stuff. So these things it's great. Really, really good library. And yeah, so some things that are useful if you want to learn more about the deep roots of this, I would suggest like the Transformer Circuits site. I've got a few things here that kind of talk about the mechanistic interpretability of trying to understand what the heck's going on these side of these things. Anthropic is far none the best at this, outside of like Luther AI. I think that's another good company that's good for that sort of thing. And then obviously 3 Blue, 1 Brown. I suggest that as well. And yeah, that's the fire hose. I guess questions, comments, musings.
Thank you so much, Josh.
All right, I'll look at the chat here. Do not trust the humans either. Yes. Reliable chain of thought, not reliable at all. So think about the chain of thought as basically it's extending out the distribution to give it more time to sample. So it's almost like thinking about how you're adding additional steps inside of like a flow matching, rectified flow differential equation. And so it's giving it more space. And they're certainly useful. They can give us some inclination that something funky is going on with the model. So it's better that we have them than we don't have them. But you should not trust them whatsoever, because there's already research out showing them hiding things deeper under the chain of thought. Let's see, infrastructure costs of running.
Oh, yeah.
Oh, go ahead.
I was going to call your attention to that. Go ahead.
So infrastructure cost of running such models. So a Gemma, I can run Gemma on my laptop here. So it can be very, very cheap. All the ones that I talk about open source today are accessible on like a 4090, something like that. I'm sure you could go lower, but for useful applications, that would be kind of where I'd start. Intended parameters into a single chat prompt to send. It can be. So having a list of prompts that you kind of take around, especially if it's tuned to that model, can be very. And being able to refresh chat windows instead of trying to keep it going. Like this is my special chat that I have with ChatGPT. That's from November of 2024. That's not so good. There's lots of bad things you might not be noticing that's happening in that chat. Yes, 10 million. Yes, we are definitely at 10 million. We're actually at infinite attention with ring attention, but it all has some funny, things that kind of go on in there, which hides it.
I'll have to ask
But all
you
right.
offline how retention works. I haven't heard of that. So, any
Sorcery.
other questions for Josh? Would you mind uploading your slides to a Google Doc or a Google Drive that we have set up for materials for the workshop?
Yeah, sure.
I will certainly go back over them with a fine-tooth comb and explore your links and such.
Very good. Well, thank you for letting me yap.
Yep, good to see you.
Yeah.
Right. I'm actually. So, Kelly, did you want to say something?
There, I was blocked. Somebody was blocking me from getting into the. No, you're up next. We can
Yep.
go ahead and continue.
Okay. Yeah, I didn't know. I had actually closed the schedule because I was going to screen share, so I've been closing
Right.
a bunch of things on my computer. And
You're formally up until if we keep on time till 2:20, and we'll have a 10-minute break at that point.
okay. So here's
Okay.
what I would like to do. So we got a live Google Colab demonstration. I would like to do a live demonstration of Claude Code, which is a terminal-based agentic programming technique. But I'm not doing the demonstration. You all are. So what I'd like to do, I'm going to set this up. In a moment, things may get a little bit tougher because we're going to do some visualization. But you may either talk to me by typing in chat or by just walking up onto the green carpet in the front of the room and saying stuff over your microphones. We're going to build a physics simulation together, and you're going to tell me what we're simulating. So I'm going to screen share here. Well, for now, I'll just share this one window. Give me a sec here. So you all should see a terminal window. Is that right?
Yep.
So the Claude Code is essentially Anthropic's LLM Claude plugged into the ability to run terminal commands. There are a bunch of safeguards around it, which we can talk about, stopping it from doing anything like sending my online banking information to, people who shouldn't have it. But I just want to show you all this tool, and it's not really, my intent here is not to do any sort of whiz bang, let me promote a certain tool that I use. Really what I want to do with you all is just explore how these things work and what they are capable of. So what do we want to do? What physics models are we trying to create? What do we like? Are we trying to do? I don't know, elasticity, vibrations, molecular dynamics. What sort of physics are we up to? You all dictate and I will drive. Three-body planet motion. Okay, so actually the first thing that I'm going to do is I wrote actually we'll use their tool to do this. Before we do this, so as Josh said, these tools don't have any memory. So the only thing that this thing can remember is what's in its context window or any notes we give it. So I've actually pasted a little bit of instructions for it here. which will save in its memory, right? You can read them, what I've just written. So Andrew, Paul, and James have given us some things that we can do. And I like damped-driven simple harmonic oscillator is cool, but I think three-body planet motion is maybe cooler because it will allow us to look at some ideas that are really only accessible through computation. Although I guess damp-driven SHO shows chaos as well. Maybe we'll do them both. So let's see. We're going to build a physics simulation of three-body gravitational dynamics. Before writing any code, discuss what is involved in this process. Okay, let's see what it says. Can everybody read the text okay over the screen share?
Yeah, I can anyway. If I
Okay.
can, I think everybody can.
So it is not revealing to me all of its internal monologue. I can look at it, right? But it's creating some tokens here. These are tokens that the model is reading and writing, and it's doing some stuff that I don't see all of because it's thinking to itself. All right, so it has spat up a whole bunch of stuff. It says it has written something called three-body design notes.md, which is some markdown file. It says, all right, we've got Newton's law of gravity. Here's how it works. It's chaotic, right? Which is why you all asked me to do this. Here's how we do this. Here's some physics. We're going to need to do numerical integration. Hey, we need to think about how to do this. We could use Euler. We could use Verlet leapfrog. We can use, a non-symplectic but higher order thing. Hey, maybe we could do adaptive time step. And now we're thinking about visualization. Okay, so let's right now, let's get it started doing things. I would like to. Okay, so now that's its notes for itself. It likes to make itself to-do lists. So now it is asking us some questions. So I'd like you all to muse on the answers to questions 1 through 4 that it wants you to answer, so we can tell it how it should write its code. Tharva says Python is best and most popular. Okay. One, the people here want to use Python because Parseltongue is a popular language. 2, 3, we'll explore lots of initial. I don't know if I have a Fortran interpreter on my computer. We'll translate it into Fortran in a minute. Conditions and time. 4, I have a real-time. Well, we'll say let's make it flexible so we can control this balance. I'll say you suggested adaptive time step shenanigans. Okay. So I told it to do all of these things. Now, it recognizes the Harry Potter reference, right? So now it's starting to work on code. One of the things about this tool is there is plan mode versus code mode. If you put it in plan mode, which I'm cycling down at the bottom, it will not write any code, not change anything, and only tell you what it is, the plan that it will implement. And basically, you can use this to watch what it's thinking about and see if it's going to do something that you want it to do or not. Because if it proposes something you don't want, then you can say, no, think of something else. So it's written 2,000 tokens here. Okay, we've got a whole bunch of stuff. So here's some code we have written that's maybe more object-oriented than we need. So here's a question for the crowd. Do we want to have this very object-oriented approach, or do we want it to do something that's maybe... Oh, that's done. RK4, okay. Do we want to create this, or do we want to tell it to do something different? No, not object. Okay. Glenda wants to run it. Yeah, so let's see what this does. Larry, I agree with you. I think this sort of object-oriented thing is a little bit overwrought. In the meantime, I'm going to change the way I'm doing screen share to share my entire screen. So obviously this is not doing what we want, but now I can switch between tabs. Okay. So it's making a visualization script that I already have in my back pocket. Oh, it wrote Arcade4 itself. We're gonna tell it to do visualization different. So Sean, I'm gonna create a new window. Here's the code that it wrote, and it has, in fact, implemented RK4 itself, right? You're calculating the 4 slopes, K1, K2, K3, K4, and then we are doing a weighted average of those 4 slopes in order to get what we want. So yeah, it's just implemented RK4 itself. So okay. So it says, want to run it and see how it looks? So let's do that. What have you written? Sure. What command I use? I don't know if you've put in required command line parameters or not. Oh, so it's got to check its code to see how to run it because, it could store all of the code in context, or it could just go look at it again. It seems to be happy to just go look at it again. And I've noticed, I usually use this with C code. I've noticed that that's a little bit slower in thinking about Python. Okay, so we just run it. So let's take this. Boop. Okay, so here are our 3-body dynamics. Now it has given us a system that is analytically stable. So here it's doing what it's doing. I'm just going back to look at chat. What next should I ask it to do? Oh, we're seeing some drift here, right? We're seeing that the time step is not quite small enough to give us the analytic solution forever, right? Right. We're already diverging from the analytic solution because the 3-body thing doesn't have something that is stable. So now we're getting 3-body chaos, even though the initial solution the initial conditions were analytically stable. Looks like we have these two bodies that are more tightly bound. Whoop, red guy's getting close to the green guy. So clearly this works, right? Good job there, robot. me to go back to GatherTown. What else would you all like me to ask it to do? Can we ask it to analyze the chaotic motion? How about we have a parameter slider for each body to control their masses? So, well, let's see if we could make sliders. I'm going to ask it, what approach did you use to create this visualization? We can certainly let it make command line parameters for us. I don't know if it could make a slider because I'm not quite, I don't use Python for visualization, so I'm not sure how it did what it did. Evaluate fractional energy error versus time. That's a great idea, Craig. So it is thinking, okay, it has told us how to do this. It's using matplotlib animation, timer-based callback system, all kinds of things. So I want to actually, I'm going to do something else. Well, actually, no, I'm going to do what you asked for right away. Oh, we have a big blip in the total energy, right? Two bodies got close to one another. So let's tell it to do that. Sure. Could you add a graph of fractional energy error versus time? First, think about how to make both small and large fractional errors apparent. I'm doing this to sort of demonstrate. So the thing that we would do, right, is we would plot fractional error, energy error on a semi-log axis. They specifically asked me how to think about how to do this. That can span many orders of magnitude. Okay, so it said, hey, wait a minute. The fractional error could be positive or negative. Log scale only works for positive values. It's suggesting that we use a symmetric log scale. Okay. I like the idea of a symmetric log scale. And it thinks so too, right? It says, this is the best idea. And it has given us a plan for using symmetric log. All right. Do it. And it is predicting what we will see. It says we're going to see errors that come from machine precision. It's going to show us, then dynamic errors that are either acceptable or concerning, and whether they are systematic or oscillatory. All right. So now it's thinking about this. In the background, I'm going to do something. Okay, so we are coding, and it's thinking to itself. So here, red is stuff it has deleted from the code. Green is stuff that it has added to the code, and it's using sort of the diff format that Git likes to use. We're still thinking. I am interested at how much more verbose. Oh, Sean, I just saw the second part of your comment. I'm sorry. You want it to do Lyapunov exponents. So Sean, there are two ways that you can use this tool. One of them is pay per token through API credits, where you pay a certain amount of money per token in, a certain amount of money per token out. You could also use a monthly subscription plan. I decided to just go ahead and subscribe to the paid subscription plan because I feel like I need to learn more about how AI works. So that means just using it more. So I said, yeah, I'm going to pay you per month. One of the things about Anthropic, the company that does this, is people sometimes criticize them of having a higher cost than, let's see what it's going to do here, higher cost than some of the other companies. I think it's because they're not really doing any sort of loss leader model. They're charging their actual costs to people. But the use it a little bit. So the way their monthly subscription works is you have a usage limit that resets every 6 hours, and the lowest tier is like $15 a month. Okay, so now this is saying, oh, there's a linear to log transition, right? This is a normal Semlog thing. All right, you've done some blitting stuff on matplotlib animation, whatever. All right. So now let's make this go. We got some Python messages. All right. So let's just see what happens in this energy conservation graph. So it looks like energy is still being conserved quite well. While it's thinking, I'm going to go back and check to see what you all have typed. Okay, so this is interesting. We're getting these spikes in energy conservation. I run the risk of getting distracted by cool physics because I don't understand why it's doing that. That's probably a near approach. Yeah, that's the near approach between those guys. And it sort of set up a stoplight color scheme there. We're about to have a close approach there. Yeah, okay. There, something happened. We incurred a pretty big energy error from that close approach, right? So it's doing exactly what we would expect it to do. Here I want to sort of show off. So I have a custom visualization tool that it is on the internet. You can read documentation for it, but this tool is not specifically trained in using it. So I'm going to tell it, you will find documentation in this directory for a custom animation tool called Anim that will let you make high performance OpenGL animations in 3D. See anim manual.txt or the docs. Make a new version of this code that uses 3 dimensions, uses anim or its output. Now, it's never seen this tool before. I'm asking it to read documentation for a thing that is not part of the training, figure out how to use it, and then refactor its code to use that. You'll notice this message approaching Opus usage limit. So the way that their subscription works is there are 2 models, Opus and Sonnet. Opus is the smarter one, and it will use Opus up to, using Opus costs 5 times as much towards your limit. It will use Opus for 20% of your limit and then switch back to Sonnet, which is the less smart. Really, Sonnet could do all of these things. We don't actually need the extra intelligence. That's just making it go slower. So while it's thinking, let's go back and look at our. Okay, so the energy conservation is now going to stay here forever, I think, because now the system has come unbound. Okay. Let's read the text. So I have told it. Okay, it's done a lot of things when we weren't looking for it, looking at it. Here it is. So I said, read the manual. And it has read my documentation and says, this is an animation tool that reads text commands from standard input. Now it's creating something that will output to it. It's doing its code. It has figured out what it wants to write. Yes. So Eugenio, you absolutely can. It will fall back to Sonnet automatically, and as soon as it gets done doing what it's going to do, I'm going to switch it to Sonnet just because that's faster. So it has written it's made some notes for it. Oh, it's done. Okay. Model, we'll switch you to Sonnet. Oh, I had it on Opus all the time. So we'll switch to Sonnet. And let's see what your code does. Okay, it's barfing forth what looks like text for my animator. That was way faster than it needed to be. So one of the things about Anim is that it performs really well. So this works. However, it's way too fast for us to see. Could you that ought to do this faster. Yes, Opus is too smart for its own good. Yes, Josh. Okay, so he just did this right away. So now let's see what it has done. Okay, so it's giving us lines between our bodies. That's maybe a little slower than it needs to be. When it's giving us a frames per step, it's telling us how to control it. Good. All right, so is this thing moving in 3D? Yes, but they're all in a plane. Are they? Not quite. Yeah, okay, so here's some chaotic motion that we've gotten. Now, it has had to read the documentation to know how to do all of this. I should point out. Okay, we had a question earlier about Lyapunov exponents. So let's tell it to do that. Okay, this is impressive. Now, do the following. Create code to
Hey, Walter.
Yep.
Just be aware, it's about 2 minutes to our planned break. I mean, we could,
Okay.
of course, go on with this for a long time, but
Yeah.
I think you've communicated very, very well here and shown a lot of cool stuff.
And we could keep doing physics forever, right?
Yes, of course.
But the point is that so what's the take? The point is that there are these tools that you can communicate with text. You can type to them what you want them to do, and they will do that for you. It has told us what a Lyapunov exponent is. This is slower than it often is, just because we were using Opus, as Josh points out. I didn't realize I had it set to Opus. It's put in some math to do that, and it will just go on. So now the big question, now that I've done this demo, is in the context of a world where this exists, what does programming look like? What does physics education look like? What does computational physics education look like? And how do we want our students to engage with a world where robots can do this? Again, this is not just like writing one line of code. This is, it didn't even occur to us to ask, does this thing know what a Lyapunov exponent is? And I mean, it's talking about like creating a shadow system to measure the divergence, I imagine. It's probably going to do some sort of fit. Like, we'll see what comes out. So,
Okay, well, thank you all.
or anything.
Yeah, very enlightening. So everyone, let's take a break. If you want to continue in the chat during the break, we'll come back with our next presenter at 2:30. All right, that's 10 minutes from now. If you want to continue in the chat room, I say go ahead. There's still some questions and some comments that are outstanding there. So, all right. So let's call this break, and I'll yell at you all in about 10 minutes here.
Yeah. So, Patricia, just as a quick thing to your question, humans guide computational thinking. What I've noticed is that these tools are very hard to use if you don't know what you're doing. If you're not aware of how they work, or how the physics works, or how the code works, you can't interact with the robot as a director. You've got to actually know what you're doing in order to use these things well. And I'll just keep tinkering while people are on break to see what we have come up with. Oh, we have something wrong. Code doesn't work. So this is another thing. They will help you debug. I have, yes, Floyd, and that's exactly what's going on. The robots are getting better at understanding us. You don't have to be, you can use just standard
Hey, Larry,
language.
can you hear me?
One of the things that I've noticed here is it knows that the output is a visualization. It can't test it because it can't see the visualization.
It's a little bit more visual, like graphical interface compared to what you were showing with everything from the terminal.
Mm-hmm.
So for me, that's personally is more user friendly for what I'm used to.
Okay.
And so and it can use various models. You can switch between some Claude models, some Gemini models, and then some OpenAI models.
So you're
And
saying,
for now, anyway, you as academics, we can get free access to Copilot if you set up an educator account, and you have to like send a picture of your faculty ID or student ID. I don't know if they're gonna make that not free at some point, but for now it's free. And so you can do it can be very similar to how you were using it, but there's different modes. You can turn on ask mode, so that's kind of what you were showing, which is like get it to think about how to do things. You can turn it on to edit mode, where it just edits your code, and then you can even turn on agent mode, where it will then try to it'll run things and kind of say, oh, I'm getting an error here. That's because, I need to do this, and kind of automatically check. Um, so now you always have to, it doesn't execute things until you say, yes, go ahead and execute that. So it doesn't like completely take over. But so I wonder, I kind of, let's see what's on my laptop. Okay. Um, I could share my screen to show what it looks like. Um, so it's a little bit more of a chat type interface. Share screen. All right.
While he's setting that up, I'll
Right.
just add in real quick that a lot of this depends on how, what student population you're talking to, right? So in Walter's case, because I know Walter a little bit, I know that he likes, one of those things he wants his students to learn is how to interact with a command line interface. And so, this works through the command line. When I teach computational physics, I am much more in the Colab, Jupyter Notebook style, which Colab is actually becoming an IDE, whether you want it to or not. But anyway, but a lot of it depends on your population. I find that my computer science students, they almost all migrate to VS Code, because that's what they learned in their computer science classes, and that's where they feel comfortable and they like it there. My physics majors all tend to stick with Jupyter Notebooks, and just different populations have sort of different interests.
Hey guys, I'm gonna suggest we continue in the chat. All right, okay? We're gonna keep on going. One thing I want to point out before I bring Atharva up is there's don't forget there's that little icon in the lower right. It says info board, and once again I want to draw your attention to part of it. It says groups. If you scroll down about halfway down, it says groups, and there's 1, 2, 3, 4, and it's actually their number. The numbers correspond to those little carpets at the top there, and that describes what the topic of each group. If it turns out that one group is particularly popular and large, we'll split that off. All right. Larry's going to put remind you of this, but I just wanted to show you this and remind you that it's here. And you can look and you might peruse that and think about what you would like to focus on this afternoon. We're going to have a little small group session starting at 3:10. All right, so just take a peek at that. We'll go over it again shortly. Atharva, can you step up into the front there on the green? So I'm going to introduce, this is our next presenter. Like Joshua, he's new to the PICUP group. From what I understand, you just finished your PhD at UT Austin, correct?
UT Arlington.
Arlington. Oh boy,
Yes.
I already screwed up the California thing. I don't want to screw up the Texas one now. All right, UT Arlington, and you're headed to MIT for a postdoc this fall. Is that correct?
Yes, that's correct.
Okay, good. Atharva, take it. How do you pronounce your last name, by the way?
Dange.
Dange. Okay, good. You're go ahead and take it away.
All right. So I'm new to this platform. I've been using Teams and Zooms, but let me check. I'll share my screen.
It's that little button with the up pointing arrow there.
Got it. And I hope everyone can see it now.
Yep. Got it.
All right. So I'm just going to cut my video off so that we all can concentrate on my slideshow. Let me see if there's a way I can present my entire slideshow instead of just what you're seeing right now. All right, there you go.
Yep, you can see it.
And
perfect.
then when I move the slides, you can see that I'm on the
Yep.
next slide, right?
Yep.
All right, so thanks, Kelly, for introducing myself. I'm Atharva, and I just recently finished my PhD at UT Arlington. It's my first time at PICUP, and I hope to be there in the future sessions as well. Thank you, everyone, for participating, and I'm excited to talk today about computational grounded theory to enhance physics education and physics learning. Please feel free to interrupt me anytime you have any questions. Or maybe Kelly can also let me know if anyone has any questions in the chat. So just to give you a brief introduction or a context of what I'm going to be talking about, here is the timeline where we started from and where we are headed. Where in the 1960s and 70s, we had the emergence of physics education research, which was the systematic study of how students learn physics and the best teaching methods to improve their understanding. It began at the University of Washington with Robert Karplus and McDermott. And the goal was to address the conceptual difficulties students faced. And Robert Karplus actually was a theoretical physicist working in QED before he shifted his focus to education. Then in the 70s came the AI Plato system, which was the program logic for automatic teaching operations at the University of Illinois, which is UIUC today. And it was the first generalized computer assistant instructional system. And it ran for about roughly 4 decades and was a pioneer of many educational technology products like having a touch screen, having a chat interface, and it even had multiplayer computer games. So teachers have been disillusioned with computer games from 1970s till today. And so in the 90s, while tech was improving, at the same time, there were these other findings which were also making headlines. Things like the FCI test by Hastings and active learning by Mazur, with the help of the eye clickers, which we are all very familiar with today. Live demonstrations to teach science, etc. And these other enhancements were also taking place at the same time. And then in the next 2 decades, there was this explosion of intelligent tutoring systems or homework learning forms, where the goal was to try to imitate human tutors and to provide immediate and customized instruction or feedback to learners, usually without requiring the intervention of the teacher. So, for example, here was this Andes system at Pittsburgh, and I believe this is a screenshot. So, and I believe this is a screenshot of resolving vectors being solved on the system using force body diagrams. And then finally, here we are today, where we not only have intelligent tutoring systems, but now we have something known as artificially intelligent tutoring systems. And this is really the next big thing in education, where it will not only change how we teach, but it will also add on to how the previous decades brought in their changes. And now the question is, how do we proceed from here, and what do we do next with AI in education? So this was this recent study in 2024 from Keston Miller and etc. from Harvard, where they showed that students learn more than twice as much when they engage with the same content during an actively taught science course versus a science course which was taught with the help of AI. And students actually spent less time on the task itself while scoring twice as much. So, of course, looking at these studies, it sounds very promising, and lots of instructors and educators are experimenting on such systems to figure out where we are headed next and what's the goal, and how do we actually help students explain and understand the work which we have been teaching so far. So with that context in mind, my motivation was to figure out if we can teach physics fully asynchronously. So this was a 1-year study where I started with virtual synchronous spring 2024, and then in the fall of 2024, in the full academic year, it was a fully asynchronous course. And the goal was that it was a modern physics course at University of Texas at Arlington, with brand new video lectures, updated homework assignments, all integrated within the Canvas system. The differences lied in the fact that we used Gen AI and a rudimentary form of repetition, where we allowed students to interact with the AI and then be allowed to redo their homework. And then we took the average of the two homeworks. such that we find some kind of learning improvement or normalized gains in the instruction with the help of spaced repetition. So the green is the spring, which stands for spring green, and the yellow is the fall yellow, which is the fall 2024 virtual asynchronous modality. And the differences from the previous 2021 semesters was that we started with a fresh focus on student learning objectives, where the SLOs are a clear and measurable statement that assess a particular knowledge or skill. They guide both the teaching methods and the assessment methods, and make sure that there is a good balance between the two, between what material is going to be tested and what material is going to be covered in the class. So here is an example at the bottom here of this slide of a clear student learning objective. For example, for modern physics, it was use nucleon charge and number conservation laws to balance nuclear reactions. So we defined student learning objectives for each module within our semester. There were a total of 13 modules or chapters. There were a total of 54 student learning objectives created, averaging about 6 per module. And then we used ChatGPT 3.5. We started with 3.5 because that was the latest accessible, free to use one at that time for us. And then eventually we transitioned to 4.0 to generate questions aligned with these objectives. And then we critiqued the questions and the quizzes we created to make sure that they are all relevant to the learning objectives and that the AI is not hallucinating. So in total, we generated 478 homework questions corresponding to 13 modules. And each module represented certain topics within the class of modern physics, like relativity, quantum theory, nuclear energy, cosmology, radioactivity, etc. We found out that there were high error rates in the generated questions, with about 60% requiring some kind of revision or outright rejection. There were two types of errors which we categorized, such as inappropriate answer options. For instance, a question on photoelectric effect, there was an option on wavelength, there was an option on color, and then there was an option on frequency, where the AI was unable to distinguish that all three mean the same thing. So all three could potentially be the right answer. So that's a question which had inappropriate answer options. And then, of course, you had the second category, which was completely wrong or just meaningless questions. And then a further categorization was achieved between numerical and conceptual questions. And in total, we had about 187 remaining, where we rejected 291 out of 478. And the 187 which we kept, the breakdown was we had 123 numerical plus 64 conceptual questions. Then we did the accuracy metrics and analysis of these questions to make sure that these questions are useful for the students between their study, and we also did a control comparison with the physics textbook where the homework was given in the previous semesters, to figure out which homework method is better when it comes to students' normalized gains. And we also did a study where what if students had used Google to try to solve these questions which the AI has generated for us, and Google achieved only a 27% accuracy on the AI generated questions versus 77 on the course textbook. So if students are using Google to try to answer homework questions, they will get a 77% on average if the homework is coming from the textbook, versus only 27% if it's coming from AI. And ChatGPT consistently outperforms Google across all methods. And then finally, in the fall of 2024, we created a study buddy chatbot to help simulate these student interactions. And students were able to use this chatbot through Canvas anytime and through any device. And this chatbot was specifically trained on these AI generated questions and on the student learning objectives, as well as the physics textbook and all other relevant materials and documents like class syllabus, all the assignments, etc., to ensure that the chatbot is well trained to respond to student queries and questions. So here are two examples where we have the fifth learning objective of relativity, which was chapter 1, where the learning objective was use the Lorentz factor to calculate the relativistic momentum of a moving object. And then the automatic question generation, or AQG for short, spits out this question for us with these following options, and the asterisk is the correct answer. And then similarly, here's another student learning objective on the Bohr hydrogen, which is chapter 2 on early quantum theory, which gives us this relevant question for to use as a homework. All right. So far we generated the questions, but now the next step was to create an asynchronous version of this course. But how? Physics, as we know, is learned better in classrooms, interacting with other people and students in the class. Well, the interaction part is true, but is there a way to substitute these interactions with the help of a chatbot, where the student engages with the chatbot, and then the chatbot provides guidance and the AI offers explanation and support? The student learns and understands, and then it can ask more questions to seek further clarification and insight. So the chatbot, as we created it, how does it work? Others in the morning talked about how ChatGPT works in general, where we have the pre-trained LLM coming from its parameters and data which OpenAI provides. This is our regular ChatGPT, and this is the user, our student on the other end, where it sends a question, but we take that question and we create a vector database filled with all our extended knowledge database, things like student syllabus, our learning objectives, like I just said before, and all our homework questions and their answers. It uses a system known as RAG. After getting it all embedded into the vector database, sends it to ChatGPT or the OpenAI API system which we created. And then after doing all that, it gives back a response to the user. So that's like a schematic of how our chatbot works, big picture wise. And of course, if anyone has any questions, we can also go through the details of how this exactly worked. So talking a little bit about what embeddings actually are, where they are vector representations of text to capture semantic meaning. So for example, if we have this sentence, Mary is helping her husband, it goes through a process of tokenization. And tokenization does not mean that it's breaking this sentence up into its words. So this sentence has 1, 2, 3, 4, 5 words. So that does not mean it would have 5 tokens. Tokenization is something which is breaking up the sentence into such chunks that each chunk has a semantic meaning to it. So for example, capital M is a separate token because capital M refers to a proper noun. And so is, for example, the letters ing, which refers to the present continuous tense. And punctuations can also be part of the tokenization process, where periods or exclamation marks or question marks may have different meanings when placed at the end of sentences. So after we tokenize this, you take each word and you create a vector embedding of it, which is a fancy way of saying you convert it into a bunch of numbers. And this is a vector of 1536 length. So the word husband is denoted by approximately 1500 numbers. And this happens for every word in that sentence. So what do we do with this vector length now? What do we do with this vector embedding? You map it onto some high dimensional space. This is a high dimensional space of 1536 dimensions, where husband is somewhere on this high dimensional plane. Now, ChatGPT knows husband exists here, and ChatGPT also knows wife exists somewhere also on this plane. And the difference between the two is the genderness vector. So for example, if tomorrow someone asks it, what is the female equivalent of monk? And to get the female equivalent of monk, remember, ChatGPT does not understand the meaning of the words like humans do. It works through these embeddings. It takes this genderness vector and looks at the exact length difference between husband and wife, and then reaches to none as the correct answer. That's how vector embeddings work. And so it's able to, using a softmax function, able to use probabilistic densities to generate answers in a human to a human with a human interface. This was the UTA Study Buddy bot. This is what it looked like. This was our interface where students could access it through any device. And you click on Start Chat. And then this is an example of a question which students wanted to know how to answer. And the main thing was that we did not create the chatbot to just give the answers to the students outright. It was, the system prompting was such that it sometimes gave random answers, sometimes it even gave wrong answers, because it was not meant as a substitute to just give answers to the students. It was meant as a substitute for peer learning, as a substitute for the student interactions which happen in a classroom. So it was designed to give multiple responses or sometimes even wrong answers. So in this length contraction question, it's actually giving you two answers, length contraction as well as length dilation, each with its own set of formulas and own set of math. Just like how distractor answers are there within multiple choice. And then you can ask any number of follow-up questions. You can ask it to show math and it would give you the right math, and math which looks right but is not. And then you have to work on the questions by talking to it and figuring out for yourself what do you think is the better approach to solve this question.
Hey, Atharva?
Yes.
Can you finish up in about 2 minutes?
Yes, I'm almost done. Yes.
Okay. Yep. I just a 2-minute warning. Go ahead.
Yes. So the CGT pipeline works like this, where you have textual data, you clean the sentences, you vector embed it, and then you have a pattern. Then you put it into the pattern recognition system, where you use a dimension reduction algorithm, and then you use a clustering machine learning technique to cluster the data to figure out what exactly the students were talking about. And then finally, you confirm whether what you did was right with different machine learning techniques like tenfold cross-validation. And of course, there's a human inspection, which happens at the end. So the clean data looks like this, all the sentences and the chatbot dialogues between the students and the chatbot. You embed it. And then after you embed it, you use machine learning to cluster it. And then you figure out the themes and the trends of what happened in the class and what students talked about in the class. This is the cluster map where the majority of students on what they talked about, which was topic 0, the orange one, was nothing related to physics, but just students and the chatbot talking to each other about things not physics, like what movies they watched, giving chatbot the personal names, and just having fun with the chatbot. And this cluster map signifies or shows us that this way of interaction was successful in creating a substitute for peer learning with the help of an AI, in order to allow students to continue interacting in the classes even though they're not inside a classroom. And then finally, the last slide shows us the significance of our work, where this map, which shows us the sum total of how common student questions were based around the macro themes. And this graph gives us knowledge on how to spend our energies in teaching modern physics in the future, or any other class for that matter, based on what students ask the most and where our attention must be focused. And for example, where students' majority theme in modern physics was energy, fusion, and forces, and the themes change depending on the groupings of what the questions were, where you also have other themes like relativistic kinematics, nuclear processes and oscillators, and the final smallest theme in the class was the quantum structure and atomic descriptions. So that's computational grounded theory in a nutshell, where you use machine learning techniques and AI algorithms with the help of a chatbot to understand what's going on in your classroom to help students interact with a system without having to necessarily be in the classroom. And finally, allow instructors to focus their energies and attentions to what works the best and what works the least, and adapt their instructional strategies. Thank you.
Very good, Starva. Thank you. I think we'll save questions for the chat or a little bit later when we break up into groups. Okay. Very, very interesting. Okay, Patricia, have you stepped up into the up to one of the podiums there? What's the plural of podium? There you go. I had to ask a silly question to kill time while you came up to the podium. All right, good. Are you ready?
Well,
All right, this is Patricia. UC Merced. It is the California University system.
yeah.
Yes. We're none of
Yes.
those state guys, you know. I mean, that's
I need to figure out how to share screen.
There's a little button. See the arrow, upward pointing arrow at the bottom there?
Yes, and then give me 1 second. I wonder if I made the right choice.
Yep, we can see it. You're on.
Okay. So this is a very short talk, different spirit as what I've seen in this session so far. What I want to do is share my perspective as physics faculty that is now a novice academic administrator, and how I've seen the support to the use of these technologies happens in the campus. I want to share with an overall perspective of how I think of education. My ultimate goal is to deliver or create and deliver a transformed intellectual engagement in the students. What I want to do today is to engage in a conversation. This is a collection of thoughts that any hardcore scholarship, as we saw in the previous talk. So in general, what I want to do is to share the resources I've seen people use to adopt artificial intelligence, AI, and LLM-based tools. So a little bit about me. I am the type of physics instructor that needs to refresh and reinvent as often as I need. And of course, when ChatGPT came out, I got super curious, right? How to use it and how I could bring it to the classroom, kind of to make it fun for me and hopefully transformative to the students. So for example, in my intro physics lab, I had about 200 students. I prompted the students to use ChatGPT to craft a short narrative about electric circuits and how electric circuits can be used to model biological processes. That was a part of the final lab report that students had to do. And as part of the prompt, the students had to critique the output that ChatGPT provided. I did that exercise for fun. 200 students. Guess what? I read. I am the type of teacher that reads the lab reports that the students submit. And not surprisingly, the students that had demonstrated kind of thoughtful engagement reported an interesting critique on the output of ChatGPT. And the students who demonstrate not strong engagement, my fault, didn't do a good job in critiquing the output of ChatGPT. So That was 2 or 3 years ago, and I said I will not do it again. And then for my upper level thermodynamics course, what I did is I prompted my students to put together a computational essay instead of a final exam. My students develop computational essay. I provide lots of scaffolding, and I told them that they were welcome to use ChatGPT to develop the code. And based on my assessment, I think they did not. Probably I don't know why, I didn't ask. I don't think there was too much engagement in using that tool. And then with my undergraduate research students, I did a couple of exercises, right? The first one was interacting with the LLM as a source to inspect our research question. That was another failure, right? We got very, very shallow answers from ChatGPT, and I was a little bit disappointed. I didn't get this interactivity and critiquing and sophistication. I didn't see that. However, in addition, because my research is purely computational, we use chat to help us with the code and also with the workflow, because we use different pieces of software. And ChatGPT never gave us the correct output, never worked. But I do recognize that based on the answers that we got from chat, with my students, we were able to craft the piece of code or the workflow that we needed. So those are examples that I used in my previous experience as physics faculty in interacting with this type of tool. So now that I am transitioning to being a novice academic administrator, what I'm seeing from this perspective is that we need to have a campus culture that supports the engagement of LLM in education. So I'm going to give you a couple of examples in the following slides. That's all I'm going to do. Examples of how I've seen the campus engages in the use of LLM. The first example comes from the Dean of Graduate Education at my current institution. We are a research-intensive institution, so there is a graduate dean. Something that they are doing, which I think is quite interesting, is to highlight how different faculty from the different schools engage in the use of LLMs. For example, what you see on the slides, I attended the talk given by the first person, Jennifer Manilay. She shared how she's in the biology department. She shares how she uses or she used ChatGPT as a teaching assistant to help her design materials for her classroom. She did not use chat to grade students or to provide feedback to students. No, she used chat to get more creative in the type of materials she uses to engage students in active learning during class time. The second example corresponds to Sylvain. He is from the Department of, I didn't write, the Department of Life Sciences, the Environmental Sciences. Yeah. So what he does is he's very into developing flipped classrooms. So what he does is he uses a collection of artificial intelligence tools to convert class notes into podcasts so that the students can listen to the podcast before they come to class. So that is his big contribution. And the last example I want to share comes from the Dean of the Graduate Division, Harand. The way he uses chat is as a refinement of his codes. Harand, for research, does theoretical computational chemistry. So he uses chat to help him debug but Haran claims that he is the one person that writes the first version of the code. So these are examples of how the institution showcases what different faculty are doing to leverage the uses of AI into the classroom. Another example that I thought very insightful is an event organized by the Center of Teaching and Learning at my current institution. What they did is they put together two different events. In one event, they kind of coach faculty into adopting LLM in their classroom. I didn't attend that event. I attended the second event, which I thought was very interesting. In the second event, we had a one morning symposium in which faculty from all the different domains of knowledge. We had, I believe we had one faculty from humanities, social sciences, physics, computer science as well. And actually we had two physicists, I believe. Two. Each faculty shared how they have incorporated the use of LLMs in their teaching. So faculty share how they help students do literature search, the example of the podcast. There was another faculty who taught us how she developed an article, a scholarly article using different searches, using LLMs. The faculty from computer science, he taught us how he developed personalized coding projects for intro to computer science students. So I guess what I want to say here is that I learned that if I want to find resonance with colleagues that are willing to try out these tools, I need to search and join what I call faculty learning communities whose ideas resonate with mine. Now, something else that I have seen on this institution is that not only faculty are supported to adopt these tools, but also the institution is helping students to learn how to use these tools. And I want to give this example that although it is not specific to physics, I think there is something that we physicists can learn from them. So in here, what I learned is that the person, her name is Bronwen, the head of the library searchers, something, I don't remember the specific title that she has. She ran a workshop for my summer research students. She ran a workshop in which she teaches students a method to interact with an LLM. The name of the method is PAIR, and I have the link on the slides, and these slides are already uploaded on the shared Google Drive. But what I found interesting is that the librarian is telling our students how they can develop a methodology to interact with the tool, a methodology that prompts iteration and reflection, which is an ideas that have been shared already with us during this workshop, a methodology that does not look for a final truth or a final product. So that way of thinking, I believe, is transferable across domains of knowledge. As another example, the librarians also deliver a workshop for our students on how to develop digital research skills, that's how they call it. So they introduce students to the different tools that they can use because they are undergraduate researchers during the summer months, different tools that the students can use to search literature, look for information, and learn, right? Learn how to navigate all that scholarship published in articles. The last example I want to share It's kind of far from physics, but the methodology is very similar. I got to learn about this initiative just yesterday. In this initiative, the Office of Small Businesses at our institution is developing a grant program to support undergraduate students. The plan is that they are going to pair up undergraduate students with owners of small businesses in the area, find a problem that the business owner is focused on, and the task of the student is to problem solve the question posed by the business owner using, this is the criteria, they have to use a large language model. So there is a methodology from the small business office that students can adopt to provide a solution to the problem. So with that, I want to share just some last words, my thinking on what we're going to do next. So this is something that I did yesterday, right? I went to Gemini and also ChatGPT, and I asked it, how can we develop a framework for students to engage in the use of LLM supported by the campus? And of course, both Gemini and ChatGPT gave me a list of stuff to do, which was not super exciting, to tell you the truth, but it was a starting point. I didn't use anything that they said. Nothing that Gemini or ChatGPT said is on these slides. But again, as I have learned in my experience, it prompted some thinking in me. So something that I reflected on is the importance of us physics faculty to reach out to different on-campus academic partners. And here I'm listing some academic partners that I have learned are willing to collaborate with us. In reaching out to them, what we can do is figuring out how they and us can work together to support students in the use of this type of new technologies. These type of units not only offer support for the students, but also support for faculty on how we can adopt this. Probably they are not physicists. Probably they're not going to tell us how to incorporate LLM in a computational physics course. I do recognize that. But I'm coming back to the previous statement. The methodology on how we interact with the tool could be transferable. In my opinion, that's what I just said. In my opinion, in my opinion, how we can use this type of tool is more as a springboard for processes, refinement, iteration, interrogation, and definitely not a source of information or finished product. Perhaps many of us have attended already many presentations on how to use LLM in the classroom, in our teaching, in our research. I've done that at the most recent session that I attended. I proposed that we should focus on prompt engineering with a Socratic framework, meaning that we probably need to define a new learning outcome or new set of learning outcomes to enhance the critical thinking and to scaffold the problem solving. The last thing I want to say, and I have learned that primarily in my new role as administrator, is that we need to argue a lot about career readiness on many programs that we develop, and certainly teaching our students how to interact with these artificial intelligence tools is part of the career readiness for them. And with that, I want to stop.
All right. Thank you, Patricia. Very enlightening. All right, folks. I'm going to turn it over to Larry. Are you? Yep, you're up here.
Yep.
I'm going to turn it over to you to to figure out how we're going to break up into our smaller groups there.
Wonderful. Thank you, Patricia. I am pasting into the chat right now the information that was also in the info board. So number 1, number 2, and number 3 correspond to the red carpet, the blue carpet, and the lime carpet. And you can think about all of the stuff that you've heard this afternoon in terms of a spectrum between less technical and more technical. So number 3, the lime carpet, is on the more technical side. Number 1, the red carpet, is on the less technical side. And number 2, the blue carpet, is sort of in between those two. And also at the bottom of the chat, the link to a Google spreadsheet has a spot that you should see your name in the left column of that spreadsheet. And then you can put information over in the column next to it of whether you're interested in number 1, number 2, or number 3. And you're invited to also put next to that a little bit of description about what it is you want to accomplish. And just to elaborate a little bit on what Kelly said earlier, so this is the way that we've done this workshop each of the last few years, that this first day on Tuesday, we give you quite a bit of information. And then at the end of today's session, get into smaller groups and give you an opportunity to talk about what it is that you want to actually get out of this and what is it that you want to accomplish. And then tomorrow, there will be the opportunity, after you've thought some more about it, to come back together with your group to talk through what it is that you're thinking about and working on. And then on Thursday, you're going to give a brief presentation about something that is of interest to you, that you are working on, that hopefully will benefit you in the fall semester for whatever classes you're teaching. Does anyone have any questions about your goal right now? So as you're getting into groups here, it looks like right now we have a bunch in the blue and a bunch in the lime, just in terms of where we're seeing people going to at the moment. We also do have the orange one over on the right. If one of the groups was too big, it could be split into 2 groups to go with some over to orange. And also, while as you start to talk about things, if you find that you want to break into subgroups, you can also use the 3 carpets that are farther down: the yellow, the purple, the dark green, and the pink. Sean, do you have a hand up? Do you have?
Yeah. Yes. Just kind of looking at the people who on the sign-up sheet. There were a lot of people like me who had similar descriptions and weren't sure if 2 or 3 was the right group. So like wanting to help students learn to use LLMs with the coding. So the coding aspect, but specifically helping students learn to use it in a useful way.
Yeah, and one way that I might think about that is if you think about what Nick showed and what Walter showed. So what Nick showed had an activity that was put in, and then looked at what the LLM gave, in that case with Gemini in the Jupyter Notebook. And Walter had a lot more of coding and iterating that was happening in his example with Claude. So I would say that perhaps Nick's example would be more number 2, and Walter's example would be more number 3. And I see Nick and Walter right there. Would you guys agree with that assessment?
I think it's definitely fluid, right? I mean, my vision, and we can of course deviate from these visions, right? But when we were planning for the workshop, my vision was that Blue Group would think mostly of issues of educational design, where the goal of the Blue Group is to develop materials to use with students. The goal of the Lime Group is to maybe our own skill development of understanding how these tools work and what they're capable of. But of course, that bleeds over into the Blue Group, because we're learning these skills so that we can use them in the classroom. So I see there being lots and lots of overlap. And it might be that in order to use, let's use the language of this workshop, that Lime Group and Blue Group have a very small separation vector in semantic vector embedding space.
And it appears now like the groups are actually shaping up pretty well in terms of having several people in each of those 3 groups. So that's great. And again, a reminder, if as you get going, you find that you want to break into a smaller group, feel free to use those other carpets on the bottom. And also, if you find that as the conversation gets going, you really think you belong in the group that's over to one side or the other side as opposed to the one you're in, you can hop over from one group to another. And a nice thing about the way this works is, unlike Zoom breakout rooms, these are much less constrained, right? That you can go in and out of groups. And you, as is happening right now, if someone is up at the front, they can talk to the entire group, but within your carpet, you will be able to discuss, and only the people within that carpet will be able to hear one another. Any other questions or comments? Oh, Ibdel, are you stuck there? Oh, you might need to click inside of the sort of avatar space in order for the arrow keys to then work. Okay, so just a quick reminder about the schedule. So what's going to happen now is, inside of these small groups, there's going to be some discussion time. So this is labeled as small groups brainstorm deliverables. So you're going to talk within the group about what it is that you want to actually produce. And then we'll get back together again at 3:40 Central Time. So that's 20 minutes from now, just to check in to see if anybody needed anything. And then for tomorrow, you can come back again it's noon Central Time to check in and discuss with your group about how you're progressing on what you're thinking. Any other questions before we completely separate into the groups? All right, enjoy.